starten noch. Okay, hello everybody. This is our last day of conference, but not necessarily the last day we see each other. A lot of people are going to be at our nice Bad Ems mine tour tomorrow. But for those that aren't going to be there, well, I hope you enjoy the last day. We also have some festivities later. We'll have the band playing, coming, Orange Green. It's made up of professors from Hochschule Rhein-Waal, so it's quite interesting. We also have a really cool workshop that Antonio will be giving to students. So later we'll be basically watching a bit on that. But before all of that, we have some really, really interesting talks today. And the very first one for today is by Eric Cosio. He's from the PUCP, which is the Pontific Catholic University of Peru. And he is director of the Institute for Nature, Earth, and Energy. He focuses on biochemistry, plant physiology, and the biochemistry of post-harvest agricultural products. And he will be talking about his AndesFlux system.
Thank you. I was just talking also to Jan, mentioning obviously the main purpose of the talks we're giving actually is to comment or to discuss a bit about emerging technologies or technologies that are becoming more usable, let's say, for the analysis of environmental problems. And I would like to return, I gave a talk 2 years ago about the beginnings of the AndesFlux network. And I would like to just show some results today and continue a bit with the information and hopefully try to sell a bit more also the methodology. So let's say that when you have a terrestrial ecosystem, the main determinants of carbon fixation through photosynthesis are essentially light, temperature, and water. When you have a tropical ecosystem like the one that's in the picture, actually the main limitation will be water, depending on what the atmospheric transport systems and the water recycling in the system are actually dependent. So this goes along with an initiative that we started close to 8 years ago, and it has been slowly materializing into both infrastructure and results, and it's involving a growing number of universities, as I put a few in the lower part of the slide. Okay, so water. The South American continent depends essentially in the central part on atmospheric transport of water that comes essentially from evaporation in the tropical Atlantic and moves westward towards the Andes. What we end up having is, let me see if this thing is working actually, no. Anyway, the westward transport will move then the clouds at high level into the Andean mountain range. And once you get that, you get a twist, and you get from the east-west movement, it becomes a north-south movement. Now, the interesting part is that although we can model, and there's been extensive modeling of the, let's say, the water balance and water requirements in the Amazonian forest in the central Amazon, where you have essentially mainly the east-west transport. It is a bit more complicated to evaluate and model atmospheric moisture transport when you have atmospheric movement along the complex topography of a mountain range that's very high. The Andean mountains are around between 4,000 to 6,000 meters around that height, and they also vary around that latitude, and they also vary in width. So what we have is that in the central part of South America, you will have a relatively narrow range that goes for about 50 to 60 kilometers in some parts. And near the Altiplano in Bolivia and Peru, you have areas that are just about over 200 kilometers to 300 kilometers in width. And that provides, and this is high altitude terrain, that provides a lot of cool air, and that influences atmospheric movement. So the summer picture would be this one, In the winter, the Atlantic cools and this flow essentially stops. So it's called the South American summer monsoon that is responsible for this movement. So basically what I mentioned that is that the north-south transport has been denominated the South American low-level jet, which is atmospheric moisture transport that runs between about 500 and about 2,500 meters, up to 3,000 meters in altitude. And this will move south. And although it is said normally that this transport on the Peruvian side and Bolivian side eventually will contribute to the hydrological balance of the La Plata Basin in the south of Brazil, as you can see from these recent models from Ventusky, you can see that actually it's only the main Amazonian part that contributes to that. And the reason is because we do have a high pressure area in the summer, the transition from summer to winter in the Bolivian highlands that actually affects transport the way you see it there. So, in view of this, there's a lot of information on the famous tipping point hypothesis for the Amazon over the next few years for the central Amazon, but we know absolutely nothing of what happens with the western Amazon. The other thing about the Amazon is it's highly heterogeneous itself. In other words, we have areas, we have extensive high precipitation seen in dark blue on one side and light blue where you have actually less. And you also have a dramatic change in dry season length. There are parts of the Amazon where you will get almost no dry season, and there are parts of the Amazon, as seen in yellow, where you can get up to 6 months of dry period there. And the vegetation adapts or is adapted to that type of regime. So the question is, if we affect moisture transport through deforestation, as is happening in the central Amazon, and we also know that we have extensive deforestation in the western part of the Amazon that's increasing. What we have is the normal ecological transition that you see in every ecology textbook that shows us that increasing reduction in precipitations and the water deficit that you will find essentially provides the so-called description of the tipping point. In other words, moving from rainforest to savanna. And this is a process that has happened in the South American continent in the past, a few million years back, and with the end of the glacial age. And usually the result has been that we have pockets of tropical forest present and a large-scale savanna. So if we want to start looking into precisely the carbon and water balance in any type of terrestrial ecosystem, there's a number of tools available for this. Many of them involve hard work in plot-like setups where you need a lot of people to measure soil respiration, to measure root growth, to measure tree width, to calculate above ground biomass, to make sure how much carbon is actually going into the soil when you put little traps, trunk respiration, and finally photosynthesis measurements that you can do directly on leaves. So these are massive campaigns that can be carried out. There's let's say, not a cheaper and definitely not a simpler way of doing it, but definitely you can also try to do it by remote sensing or averaging techniques. And that's why we have a number of satellites, including the Orbital Carbon Observatory, OCO2 and OCO3. And we have fluorescence, sun-induced fluorescence system, SIF, like the FLEX satellite that's gone up now from the European side, that permits us then an evaluation of carbon and water metabolism or cycling in these ecosystems. Another alternative also that was developed really at the end of the last century appropriately has been that of analyzing fluxes in these ecosystems. And for that you use towers. These towers are of varying height. If you're working on a savanna or in a grassland, you probably need something that's not more than 4 or 5 meters tall. When you're working in a forest where you have trees of about 35 to 40 meters tall, then you do have large structures, like the one that's shown there. But the idea is, returning to fluxes, is that they average the movement, the vertical movement of carbon and water and other trace, atmospheric trace gases. And what you're doing essentially is a calculation where you see if there's more of your carbon moving from the atmosphere into the ecosystem, you have essentially what we call a negative balance. That is, you're storing carbon in the ground. And if you have a movement from the ground to the atmosphere, then you have a positive valence. In other words, your surface is becoming an emitter of carbon for this. And for this, what you have to do essentially is do a high frequency measurement using sonic anemometers at about 10 to 20 times per second, where you're essentially checking the movement of air in vertical direction, the vertical component. And if it moves down and you have a mass analyzer, in this case, for example, an infrared gas analyzer, you know how much concentration, how much mass has moved from atmosphere down and in the other direction also. So basically that's the idea of carbon fluxes measured by eddy covariance. That is the covariance of a number of factors based on the eddies or the turbulence above a certain ecosystem. And the idea is that you measure mass and energy. So your energy balance has to also be adequate. Looking at it in a simple manner, and without trying to bother anybody with equations, what you have is a flux will be determined essentially by the average vertical movement then of CO2, water, or whatever gas we're measuring over a 30-minute period, the fluctuation in the concentration of that gas at that period of time, and the velocity of the air that's moving upwards or downwards. Those three components give us this very simplified equation that specifies what is it that we have in a flux. And that's what we will be calculating in them. However, energy comes into play. And this is a quick excursion into the energy balance. And what you have essentially is you have radiation that comes in, and radiation that comes out, and radiation that's returned. If we look at this from that other side, we have that the net radiation in this system will be in balance. That is, has been coming in has had to be re-radiated, and we have sensitive and latent heat. Sensible heat and latent heat describe the energy that's required, first of all, simply for a transition in temperature, in mass without change of phase. And the other one, which is more important, the latent one, is when you have the transfer of water into vapor, and then it goes as evaporation into the atmosphere. And of course, you have to have also the component of how much energy is stored in the soil. When we can calculate then the balance simply by saying, essentially moving this factor over here, and we should have, if we have 100% recovery in the system, this should be equal to the other term. Unfortunately, usually it is not, because there's a number of measuring factors that are involved. And the result is when one plots then the QS, QG versus QLE and QH against each other, you have essentially a linear regression, and the slope of this linear regression will be giving you the energy closure of the system. This is usually for tropical forests around 70%, and this is data from one of the towers that we have. On the left-hand side, you have hourly fluxes. On the right-hand side, you have 4-hour fluxes. That is averaging, so it makes a cleaner curve. So the resulting measurements will give you something like this hour of day plot that you see. We have, during the night, essentially, your balance is above zero, which means that the soil is respiring, the ecosystem is respiring and emitting carbon to the atmosphere. And the moment the light goes on during the day, you will start getting then negative fluxes, which imply that you're getting then carbon fixation by the system. If we add and measure exactly the balance factors that are involved there, we will see that everything that's under the red area is what's calling us what's being accumulating in the reservoir. And the green part is when you're emptying the reservoir, that is, you're reducing the CO2 that's present in the air around the ecosystem. So this is the part that's important. If this is in the, let's say, larger than the red component, the ecosystem is a net carbon fixator. And the big problem is, or the big question is, whether the Amazon is actually doing that. So, given the lack of information on the Western Amazon, precisely using these type of systems, we started about, like I mentioned, about 8 years ago, with the idea of let's start working on a flux system. And for this, we got the initiative by Professor John Grace from the University of Edinburgh in those days, and from Manuel Glor from the University of Leeds, that supported the idea and brought initial funds for this. This was like the seed fund to get it started. And we set up the tower here in the south, which is in a national reserve called Tambopata National Reserve in the south of Peru, bordering almost Bolivia. And since then on, we've just been building on that, interestingly enough, with a large number of Peruvian funds. So we have about $1.5 million invested from local Peruvian science funding into this, which has provided us with a network that's being finished this year, that was finished this year with the inauguration of a northern tower here. And we're collecting data. We have about 10 years of data from here in the south and less data from the towers in the north. But it's a network that's available. And as I will mention at the end, it's a network that's completely open for initiatives, international, or from anybody that wants to either obtain information and provide publications or that just wants to invest into this. So it's been a particularly successful period over the couple of years because it's gathered a lot of interest from a number of groups. So let me see. I'm just going to show some data from 2 of these towers, and just to mention the difficulties that we can have. The towers in the south essentially are about 100 kilometers from the widest part of the Andes, so you do have a strong Andean influence in the dry period when you get inversions and you start getting cold air into the Amazon. And here, this other tower that we have a year working in combination with the University of Bayreuth is essentially located in what we would call an alleyway for atmospheric transport. So this alleyway is located between the Andes, about 100 kilometers, but then not to be seen much here, there's a mountain range around here that's called El Sira, which are mountains that are about 1,800 meters in altitude. And what it does, it channels the low-level atmospheric flux that's moving from north to south through that area and provides sort of an interesting contrast to the towers in the south. So basically, these towers have this type of equipment. We can just divide it simply into saying there's high-frequency measurements that have to do with anemometry and CO2 and water measurements indicating fluxes. We have the infrastructure necessary for them. As you can see, we have various types of towers. There are towers that are 3 to 4 meters in diameter, and you can climb up, as Rolf has done, just as if you were in your house. And there are towers where you have just 40 centimeter, and you just have to climb them with equipment. You have mid-frequency measurements that have to do with the energy, that is inciting radiation, short wave and long wave, and how much is coming up. Also photosynthetically active radiation called PAR. And of course the normal temperature and humidity measurements, and more important, the amount of energy that's flowing into the soil in soil heat flux plates. And we have a number of low frequency equipment that is measuring essentially the partitioning of CO2, water, methane. Sorry, there's an extra 2 there. That's not hydrogen peroxide, it's water. And rain. And the big problem with these towers is once you install something, everybody wants to put something else in them. So you start getting a lot of power consumption. Just quickly, because I think, can you let me know if I'm running out, because I will stop. Okay. I'm already over? No. Okay. Seasonal patterns, just to show a bit, we have then in the summer monsoon, the South American summer monsoon, you have essentially the northern and northwestern component. Once it gets dry, you start seeing that the Andes start taking more influence. You can see also that the dry season in the south is dramatic. You can have up to monthly precipitation of the order of 400 millimeters. And when you get to the dry season, it can drop to below 20. This is in an El Nino year, where we had actually very, very low precipitation in the dry season. And the other thing is, it's important to actually characterize what's around the tower. You need to know what trees are there. Everybody mentions there's high biodiversity in tropical forests, and that's true. But that high biodiversity is reflected over a few bullies that are present in large amounts, and a large number of small trees that are just other species that do their stuff. So if we start looking at this, about 40% to 50% in some of these forests are trees that belong to about 2 to 3 families. So that's important, and if you look at, although I haven't marked it here, but these are our 4 main locations in working now. And the left-hand side is, I think my marking disappeared with the transfer to the computer here. This is a primary forest. These three are secondary forests, but some of them are older secondary forests, except this one, which is a new secondary forest. It's about 10 years old. So they have a different species distribution. One last thing before I'm running out of time, but still, is that one thing that what is observing in the Western Amazon is a replacement of hardwood trees, like these species, with palms, which means we are getting faster carbon cycling. So, just quickly, interesting here also to measure is to analyze the physiology of the forest around. We have infrared cameras pointing at the canopy. We can measure then temperature, and you can see that at the start of the day, leaf temperature is higher than air temperature, but once transpiration starts, obviously the temperature in the leaves starts dropping down. That's in dry and wet season, and that's reflected as the delta T there. The negative part where we have higher temperatures in the leaves, and the part of the day where we have lower temperatures in the leaves than air temperature. And the fluxes measure water movement, and we can measure therefore evapotranspiration in these systems. These are for 2 towers in wet and dry season. And you can see that the actual differences, and that's one of the surprising things, in absolute fluxes between dry and rainy season are not that large. In other words, the trees keep transpiring despite the fact that there's no precipitation. And that points out to some of the limitations that one might find in these forests. A bit irrelevant, but if you want to check it, because for storage purposes, one has to check the distribution of CO2. We measure essentially CO2 concentrations along the whole tower length from 42 meters up down to 0.5 meters near the soil. And you see obviously that during the day, you start getting lower concentrations than the usual atmospheric concentrations. We're getting down to 360 ppms. Actually, the current atmospheric concentration is 420. And during the night, under the canopy, you start getting values that are very high near the low level, near the soil, where it gets to almost 500 ppms. So that's the essential movement that one observes in CO2 concentrations due to photosynthetic activity. To start finishing with the stuff, we have some gross primary productivity, which is essentially the amount of carbon that comes in, but you're not subtracting respiration. And if you notice from 2017 to 2023, we're following essentially the El Nino cycles. You have more GPP when there's no El Nino, when it's La Nina or neutral, and you have less GPP when you have an El Nino process going on. So the forest follows essentially that. When you start looking simply at the difference between dry and wet season in the Tambopata area, you find again the same thing. GPP is lower in the dry season than in the wet season, normal. And if we start looking, however, at the impact of each one of these phenomena, we start finding the difference tend to be more puzzling. And that's a lot to be written, that means a lot more papers that we can get out of that. So El Nino, you can see, has a lower GPP. La Nina, it goes better. Neutral is also around. And in the wet season, those values all go up. However, this is not all the calculation. One has to measure respiration, and you can do that also with the flux system. And you have here, ignore the negative, you have more respiration in the wet season than in the dry season. Again, normal to expect. And you can see the differences in respiration rates between the 3 ENSO periods that we would have in those forests. So finally, you subtract one from the other, and you have your net ecosystem productivity, and I'm just going to show the final values. The forests are essentially neutral in that area. In other words, they're not accumulating more carbon every year. They're not releasing it. We have essentially, be it dry or wet, over the whole 2017 to 2023 period, a forest that's static with the atmosphere. So the story that the Amazon forest actually contributes effectively to this, no. Under this balance, it says it's respiring just about as much as it's fixing. And to end the talk, this is my favorite graph. We just got it this year. It was a product from Raphael Stern from Stanford that started thinking about that, and I said, okay, this is great, because there's a lot of speculation among ecologists always on seeing what is the temperature functional range of an ecosystem. And there was a paper published by a Brazilian group, unfortunately I can't remember the names right now, this year about the tolerance of temperature from the forest, from the Amazonian forest, and they said it was about a 4 to 5 degree range that we had. And if you notice here, 0 means no production basically, and below it would mean emission. And if you start looking at the areas where we have a positive value for net ecosystem production, we go from about 26 degrees to about 33 degrees in temperature. Now, this, and to finish, this is the average of all the species there. If we raise average temperatures and this shifts upward, what we will have is, if we could analyze the photosynthesis on some of the isolated major species, we can predict if that forest is going to collapse and have replacement of species present in it. So this is a very fast calculation that we've managed to do, and we're very, very happy with it. Well, to finish, so AndesFlux then is now approaching hopefully maturity. It's a sub-regional network of forest plot and ecohydrological sites spanning existing environmental gradients in the Western Amazon. It aims to provide integrated information at a scale currently unavailable for the Western Amazon. A consortium of 10 academic institutions, open to new members, initiatives, collaborations. Anybody that wants to put in a new instrument is welcome. And the network is expanding. We're still hoping, although we've been hoping about 3 years, to be able to expand into Ecuador, and I've just been making some contacts with Colombia. So thank you very much. We're hoping that with the Forschungszentrum Jülich, we will probably start checking in Tambopata a solar induced fluorescence system that will give us much more detail into that last picture that I showed. And there's a lot of people involved in this, and I would like to thank everybody, because just practically everybody has collaborated one way or another. Thank you very much.
Well, thank you very much. I think this is an excellent show of why it's so difficult to be a timekeeper, because you just want to... This is not the first talk where I wanted to listen to more, but maybe we can listen to some more during question time. Yeah, or we can do that, but maybe we can have one question, I think, at least. Yeah, I think there's a...
No. Eric, maybe it's just, I don't know. You said that there is a strong influence or dependency on the NEP, of NEP on temperature. So, and you are measuring temperature now at these spots, the towers you have, right? But is there any measurement about the temperature variation throughout the whole forest, right? You know, what are the individual temperature variations locally? And how would that influence the NEP, of course, and how would that also influence the distribution of the species?
Yeah, there's two critical factors there: air temperature, which we're monitoring, and we can probably plot over the set of years. But there's another interesting temperature, which is canopy temperature. And canopy temperature, we only have essentially pointed at one single species out there. And there was an initiative that unfortunately fell apart because a British group from the University of Leeds wanted to set up a network that's called Thermitrop. And they have then infrared cameras that are, give you the whole picture of the forest. But they sent it to Ghana, the equipment, so we'll get back at that.
Okay. Yes, so maybe other questions we'll talk about in the coffee break. So then we welcome our next speaker, which is María José Meneses Gómez. She's from the University of Costa Rica. And she's going to tell us about the comparison between the use of BMWP-CR and ICAIDEAM indexes. So she'll tell us all about what that is.
Thank you very much, Magdalena. Hello everyone. I hope this temperature increase takes you well. First, I'm gonna apologize because the English, it's not part of my main skills, so, okay. But following with the topics of environmental monitoring, I'm gonna tell you something about a project that I have the opportunity to participate as an assistant, entitled The Comparison Between the Use of BMWP-CR and ICAIDEAM Index for the determination of the water quality into rivers in Turrialba, Costa Rica. In which I work with Carlos Sanchez Romero as a main researcher, and well, go ahead. First, this is the structure in which I'm going to present the project today. The introduction, objectives, methodology, and study area, results and discussion, and finally the conclusions. Well, I'm gonna have a mini background about the why behind this research. In the specific case of the Turrialba, the water quality of its main rivers has been affected by a poor management and disposal of untreated domestic and industrial wastewater, solid waste, and runoff from agricultural activities. So that it's aggravated in the center of the canton, where the wastewater from the central area is discharged into the Turrialba and Colorado rivers without any type of treatment. So it's important to say too, the last research was done on this subject was in 2006, so it was a really long. So, the importance of this research is to create available information, because we don't care finds a lot of that, and establish a new baseline. As a general objective, we have to compare the BMWP-CR and the ICAIDEAM methods for the determining water quality in order to identify key differences in the use of each. And the specific objectives, it's to analyze the water quality through its standard regulations, and define the indices that allow to a specific recognition of water quality. And to compare the results that obtained of each indices to make difference between of each methods. As a methodology, first of all, we did some preliminary samplings where we took GPS points of the location of the basin and look for the places with a good accessibility to the sampling points. We made 6 sampling stations, 3 of them in rainy season and the other 3 in dry season, in the upper, middle, and lower basins of both rivers. Here in the figure 1, we could see the study area and the sample points. Turrialba, it's actually located here in the center of the country. And as you can see here in the map, we have the Turrialba River, it's the mark in black, and the Colorado River is this one that it's marked in blue. And the red and orange points are the basin points for the samplings. So here we have the upper points, the middle ones, and the lowest ones. And to put in context about the indices, the ICAIDEAM index index, it's about take some parameters for the water, and in order to obtain the water quality, we made some of these parameters, that it's dissolved oxygen, suspended solids, pH, electrical conductivity, and chemical oxygen demand that we could find in a standard methods. As you can see in the, that's the code of the standard method that we made. And the BMWP-CR index, it's a method that it's established by a Costa Rican degree. In order to obtain the water quality, a classification, it's made of macroinvertebrates as bioindicators of the water quality. And and finally we have the results. And here we can see, the results sustained of dissolved oxygen in the Colorado River and Turrialba River in rainy and dry season. We can see in the figure 3 that in the upper basin, we can see a low value of dissolved oxygen. In the upper basin, that it could mean a high load of organic matter. And this is the result of suspended solids. And as you can see in the figure number 5, in this case, we can see another ordinary event, which it's very normal in the rainy season to in the canton that the level of the water rise because of the rain. And for the pH, 2 in the figure 7, we can see a high level of pH that could be significant that maybe a presence of detergents or fertilizants in the water. And for the electrical conductivity, a higher value also could mines a high concentration of minerals or ions in the water, dissolved in the water, such as chloride, sulfates, nitrates, etc., for anthropogenic causes as well. And for the end, we have the COD. And in this case, the results are not bad, so it's okay. And well, for the ICAIDEAM, these are the results. So if we can see in the charts, based on the results, we have an acceptable type of quality of water, but not in the case of the middle basin, that it signifies regular quarter water. And follow with the BMWP-CR index, we have the identification of the macroinvertebrates in the water that we have, that we use this kind of chart to use for a classification of the families of macroinvertebrates that we could find in the rivers. And here we have the results. As you can see, the results are really different than comparing to the other chart. That it's a combination of pollute, very pollute, and extremely pollute quality of water. And well, here we have a resume and the comparison of the two indices. Why of this? Well, as a conclusion, the difference could be a response to the nature of the methods and the factors taken into the index, because the BMWP-CR index is related to bioindicator parameters, and the other one is physicochemical parameters, so that it's really different. The resources that we could have is the BMWP-CR needs fewer resources. You just need a good pair of eyes to classify the macroinvertebrates. Well, the combination of both methods are complementary and really necessary to have a better capacity to analyze the real condition of the water quality, because as you can see, maybe we could obtain different kind of water quality, but in the case of the ICAIDEAM, it don't takes sufficient parameters to obtain maybe more close results as a reality. So, well, I have some acknowledgement, the UCR, the Vicerrectoría de Investigación, and Latina, of course, and, well, Magdalena and Patrick that is hosting us. And, well, if you want to know something more, just contact us. That's all. Thank you very much.
Thank you very much. We have time for some questions. Yes, I already see the first one.
Hi, thank you. I was wondering, maybe if you have such a huge difference between the outcomes among the physical, chemical parameters and the biological, it makes me wonder who sets the benchmark, who defines what would be a good biological condition, and if you have had any experience with a stretch of any other river that you would consider to be pristine, an ecologically intact river to which you can make any comparison.
Well, actually, this is the first part of the investigation. After that, we make some research in other two rivers, in Turrialba Canton too. So it's really it's really curious to do that, to see it, because the results are very similar in the both cases. So yes, we have a chance to compare all of the results, and we have maybe the BMWP-CR it's better because these animals, well, could live in the water as maybe days, weeks, or a month, and so they could pueden recoger más información, more information than the parameters, because when we took the physicochemical parameters, it's like take a photo in that moment. So this animal could take more information for us. Yes.
Very interesting, thank you. Any other questions? Well, we'll certainly probably talk a bit about this in the coffee break. And thank you very much. So we'll have the coffee break until 10:45. Okay, everyone. Let's take our coffees and take our seats. Sí. Okay. Our next speaker is Franklin Ayala from Oceánicos, and well, which is part of UNAL, the National University of Colombia. He is a research assistant at the National University of Colombia. He specializes in coastal engineering and oceanography. He focuses on coastal processes, hydrodynamic studies, and nature-based solutions to combat erosions. And he's going to tell us a bit more about all of that. Thank you, Frank.
Thank you, Magdalena. Good morning, everyone. As Magdalena said, I'm Franklin Ayala. I'm coming from the Universidad Nacional de Colombia. I'm a research assistant over there. And I'm going to talk today about the coastal monitoring system based on video cameras that we are trying to bring it back to life in San Andrés Island, which is one of the main islands in Colombia. So basically, our research group is called Oceánicos, which is part of the Universidad Nacional de Colombia. And at the same time, the Universidad Nacional de Colombia is part of a consortium, or like a center of excellence in marine science that is called Semiarid, which is made of, right now, 9 Colombian universities and 2 German institutions. So even this was a photo that we took the last time that we came here to Germany to visit one of the largest wave channels in Braunschweig. So our research lines are mainly based on oceanography and coastal engineering and marine ecosystem services, marine energy, oceans and society, and of course, nature-based solutions. So as a way to introduce this topic, it's important to mention that we have a lot of things to take care of in the coastal environment. And now we have coastal hazards. As you can see in this image, this is a real image from Providencia and San Andres, when the Iota and Eta hurricane came across in 2020. So we have also some need of navigation, and also we have a lot of touristic use of the beaches in San Andres and Providencia. So basically, the decision makers are interested to know how are the resources there and the uses that we take for the coastal environment. So as a way to assist this kind of decision makers in the coastal risk management, there is some video coastal monitoring that basically started in the 80s in USA. Then the Coastal View project implemented in Europe. And now in Colombia, I'm gonna show you later that, but in Colombia was implemented by the Universidad Nacional de Colombia with the Universidad of Cantabria from Spain, and was sponsored by a Spanish agency of development. So basically, there are 2 different ways to make measurements on the coast. So we can have like site-specific measurements, like when you have this kind of wave sensors that you deploy on the deep. And also you can make some kind of array measurements when you are basically making bathymetry or topography surveys, right? So basically you have this kind of profiles along a certain beach that you are trying to monitor. But the point with that is that there is not enough spatial resolution. So that's why remote sensing and all the things related with video cameras are really, really important for the beach monitoring, especially because, yeah, they can provide this kind of high spatial resolution, and at the same time, they are cost effective, and you can, in a certain way, collect continuous data in comparison with the array-based measurements. So in the code, we have the code is a really dynamic environment, so you can have a lot of things happening at the same time. As you can see, for example, we can have wave breaking, we can have a shoreline that is really important at the time to recognize what is the maximum setup or the maximum height that can be flooded by some event. We have an intertidal profile, which is basically the beach that is covered depending on the tide that you are having during the day. And also we have vegetation. So yeah, there are a lot of things that are going over there. So we came across with this system that is called Horus. So Horus was a system that was active in 3 different places, let's say, Spain and Colombia and Germany. So basically they were working with some Stingray cameras by the Aledition, that is even is a German company, if I remember well. So the process that we were having there is basically we were doing the data collection, defining the region of interest that we needed. For example, we apply some time operators to pre-process somehow the images that we have. Then we go directly to the processing part. So basically we have to use rectification and fusion because basically we have the image in image coordinates, right? Like pixel coordinates. So we have to move to the real world coordinates. So that's why we have to do rectification and fusion as well, because they basically don't cover all the area of the beach, right? So we have to basically make the fusion for that. So later we use the post-processing stuff, which is basically we analyze the variables that we need to get or we can analyze through that kind of images, right? And then we were using information measurement for transmission, even for storage, and at the end for dissemination, right? So our case study was Cartagena, Colombia. So basically this system was working during 8 years over there. So as you can see, there are 4 different cameras that were basically covering different parts of the beach. So for the data collection, we had different type of images, let's say. So this one, for example, is a snapshot one. So basically, yeah, as the word say, is just a really quick snap of that. This one, it was a time average image. So basically, we were computing the average of the intensity for each pixel. And also, we were collecting some variant image. So maybe it's hard to see, but for example, around here, that is also around here, there are some higher values for the variance, for example. So to process basically this kind of images, as I was saying before, we have this kind of image coordinates. So basically we selected the region of interest. So basically we have to map the image coordinates to our real world coordinates in order to be able to measure the things that we want to measure at the end. So clearly we have to make the fusion. So basically the fusion is basically translating the images or moving the images to basically cover all the area that they are supposed to cover. So as you can see here, for example, this fusion of oblique images are basically taken by 3 different cameras, right? In order to get all the beach, in this case, in Boca Grande, in Cartagena. So at the end, if you rectify the images, you can get basically all the area that you are trying to measure. So at that point, you can start to compute all the variables or processes that you are interested in. So for example, the shoreline position. So The shoreline position, in this left side, for example, is the beach. Let's say in the right side is the ocean. So you have to take manual measurements as a way to validate the shoreline position. And the point is that you have, obviously, with all the data images that you need, that you have, you can start to compute what is the point where the interface from the beach and the ocean are basically are staying together or are in contact, let's say. So, for example, this one was profile elevation. This one was collected with topographic surveys, and this one was computed with the methods that by that time were not using any kind of deep learning or machine learning techniques. They were just using like traditional or conventional methods to process images, like those methods that you can see over there, like Sobel, Canny, and so on. So another thing that we can do with this kind of images is the beach user density. So the beach user density is a way to know how a beach is used or occupied over the time, and that is really or extremely important for coastal measurements. So basically it's an object detection task. So as you can see, for example, in this image, the red color means that you have less space per user, and the blue ones mean that you have more space for users. So for example, we can see here that there are more concentration of the red colors, indicated that is a more occupied area of the beach, right? So obviously these kind of images are also used over the time, so you can see day by day or time by time how this occupation is changing, right? Also, we can compute some hydrodynamic variables, which are really important as well, because as you can see here in the wave breaking zone, it's really or extremely hard to deploy a measurement device over, let's say, 2, 3, or 4 weeks, because the wave breaking is all the time moving or trying to displacing the measurement device. So there is no way to keep it fixed. So that's why, for example, the video cameras are really important, because they don't have to be, basically you can monitor from area that is farther away from the wave breaking zone. So basically if you compute or you get a transect along the shore and cross the shore for every time. So you can have this kind of plots, which are basically the variation over the time, and you get also this one in this case is the along shore and the cross shore one. So you can start to compute different kind of hydrodynamic variables that are really important for the coastal measurement. For example, here, if you get this cross shore transect and you pick some specific points, you can get the intensity of the pixel, and that intensity at the end will be a way to compute the energy power. So with that energy power, you make some fast Fourier transfer or like Fourier analysis, and you can compute, for example, the peak period of the waves that are getting or breaking on the coast, right? And also not just that kind of waves, you can also compute the infragravity waves, as you can see here, for example, because these kind of waves are extremely important for the morphologic condition of the beach, right? Like the sediment transport and other things that are basically shaping the beach. So as you can see here, for example, this example was like a peak period of 8 seconds. So this is a wave buoy that is similar, or that is near that site location, and was measurement 7 seconds. So as a way of validate quickly this kind of methods. So also we can compute like the wave celerity. So as you can see here, the wave celerity can be computed by this proportion here. So from the measurements, we got 1.8 meters per second. In this case, with this kind of images, we are getting 1.3 meters per second. So again, it's a way to compute this kind of hydrodynamic variables that are otherwise really hard to compute or really hard to measure on the coast. So yeah, this is really important, as I was mentioning before, for users, so to monitor the beach use, and also the shoreline and bathymetry conditions, and also the hydrodynamic conditions. So far, the lessons that we have learned is that the multidisciplinary collaboration is extremely required, because basically we are in Oceánicos group, so basically we are oceanographers or we are coastal engineers. So we are not electronic engineers, we are not like systems engineers, so there are a lot of things to do over there. The saline environments are really can really affect the lifespan of the measurement devices that we can deploy in this kind of conditions. Clearly, when we start to collect all the data, we start to realize that the data management can become unmanageable. So that is also an important thing that we have to take into consideration. And also there is a high potential, as I mentioned later, or I will mention later, to incorporate all the relevant measurements. So I use this example here just a way to show you how looked that kind of system 15 years back. So basically we were using the cameras that were connected to a specific computer through a firmware interface. So we were using a motherboard. It was like, I don't know, yeah, long time ago, to be honest. So we were using a cooler, a processor, a modem to get the transmission of the data, and we were trying to incorporate even energy autonomy through solar panels. So yeah, there are a lot of things that we have to change over there, especially because the current challenges that we have is this kind of ideas about edge computing, the application of deep learning techniques for all the data that we have over there. We have, you just can imagine 4 video cameras taking a photo every hour during almost 8 years. So it's a lot of data that we have there. And another challenge is the coastal vegetation monitoring and the integration with the other measurement devices. Why? Because now in the island that I will show later, in San Andres, they came up with this a device that is basically a weather station that they developed, or they developed by their own, right? As a way to get cheaper devices and also functional devices for the island. And also we can get the integration with other kind of techniques or devices that is called SNAP. I don't know if you have heard this kind of system, but basically you have a placeholder near the beach. It's kind of like a science, like citizen science initiative to basically record an image of the beach, and basically from the science part you can process this kind of images to use the models or use the techniques that you usually employ for image analysis. So also in the group we have other kind of projects, particularly in San Andres we have the mid-ocean variables monitoring. So for example here, this weather station was also developed by a group that is close to Oceánicos. We also have the buoy measurements. This one is a buoy measurement. This one is a acoustic Doppler current profiler, which is also a way to measure the waves and the current. And also we have this project that was related with coral reef building. So basically they were bricks made with 3D printed clay. So as a way to restore the coral reefs that somehow we are losing over the island. So yeah, thank you so much for attention.
Thank you very much. There's already one question.
Thank you. I was wondering, to my understanding, you're making an assessment about current state situations. You're trying to describe what the current situation is in real time at best. Are you trying any form of prediction? You trying to correlate the data that you find with other data, remote sensing in the ocean, to make predictions about the probabilities at which waves will hit at a certain strength within a given time?
Well, we would like, but in order to have a really good forecasting system, you should first have a really good hindcasting system. So now we are mainly focused on the hindcasting way. So basically the hindcasting or now casting way is being able to capture the information right now and being able to understand the processes that we have in the past in order to get better knowledge for the processes that are happening in the future. So there are some techniques or some studies that have applied this kind of images to predict the sandbar positions near the coast, which are really important for the wave breaking. But yeah, besides of that, there are not many studies about forecasting per se.
Could be one field for cooperation about deep learning that you mentioned.
Yeah, absolutely. Yeah. So with all the data that we have, basically, we can train any kind of models that currently are existing to be able to predict this. Even that study about the sandbar position was made with deep learning, with a deep learning technique. They were using a neuronal network, to understand which were the processes that were dominating this this sandbar position. Yeah.
So, thank you very much for your presentation. I'm wondering, so you showed a little bit that with the high casting that you're doing right now, you showed like the difference with one of the sensors that you have already embedded. And my question is, there was a difference of, I think, 1 second for the time of, so can you maybe just go to the, so in the frequency, there was a difference, I think, of 1 second, exactly. So one of them was 8 seconds, the other one was 7 seconds, and something like that. So my question is, how much, so what is the accuracy that you need, for example, for a remote sensing approach to have? So is that 1 second good enough? So because before you start building, for example, prediction models, you first need to check, okay, how good do I need it to get? So what would be what am I comparing it with? So that's where my question is going.
Well, this kind of video systems are mainly used for validation, the numerical models or the numerical wave models that we use normally in oceanography and coastal engineering. So not to calibrate them, just to some sort of quick validation about their performance. So based on that, 1 second in this case, for example, is not it's a really good approximation because we don't need that kind of specific accuracy from a deep learning technique, for example. So particularly because in terms of period, maybe there are some variables that you need to be more accurate, but for example, from peak periods and other kind of variables, basically they are just moving in some specific ranges. So yeah, you have that kind of range as a way to, yeah, you don't need to be that specific. So basically moving in that range can give you some sort of idea that the numerical wave model or the hydrodynamic model that you are using behind the curtain is doing well.
Just a quick question out of curiosity. It looks like some of these remote sensing, especially from images, could be probably approached also using large vision models. Since you're already talking about deep learning, do you know if that's going to be implemented? Because usually the programs that do large vision models are using static but also dynamic models, and they're being used more and more in medicine now. Would that be relevant?
Well, I guess it would, but I haven't seen any kind of language models used in this field. Yeah, so far, because yeah, they came across like 1 year ago with this like a review, immense review paper about this kind of techniques, especially coastal imagery. So yeah, I haven't seen this. Yeah, it could be useful, I'd say, but yeah, based on my knowledge, I haven't seen that kind of options explored.
Thank you. Are there any further questions? Yes.
From the very nice talk, by the way. From the camera point of view, in your future wishing list, would you like to improve in some sense the cameras you're using? Maybe a better pixel resolution or whatever? Thank you.
Well, as I mentioned before, we are trying to bring the system back to life. So now we have these, like, I don't know how to call them, like smart cameras. So basically they are able to, they have some RAM to make processes inside, even to run some AI models. So yeah, in our wishing list that could be helpful because we can start to detect the data collection with the data processing. So basically we can work more on the edge, because with the Stingray's one, they were just basically taking the photos and making the transmission to a central unit. So basically everything was centralized. So yeah, for sure we would like to employ different cameras that are avoiding this kind of centralization. So yeah.
So also one quick question from the cameras. So how free are you in terms of camera position? And because I saw, for example, on one of the pictures, I guess you're using the steel equipment that was for the projects that you mentioned. And I saw, for example, that there was also a building in the middle of the picture. So how much of a challenge it is for you, for example, like this, the fact that tourism is also overtaking, and so how much is it a challenge for you for your measurements?
Well, there are some challenges because usually we install this system on the roofs like 15 years back, especially because we were looking for a high position because, yeah, you know, the orthogonal procedures that you have to do in order to map in the images, right? So basically in our group, we have to design the structure that is holding all the cameras, but it's, let's say, free. It's basically dependent on our thoughts or how we consider that is whether good or not. So can be difficult install them like right on the beach, particularly because there are some, we have in Colombia, we have these hotels that they call the beach private. So basically you can do anything on their kind of space. So yeah, that's why we have to start to look for like companies that they are interested to have this kind of things, or the hotels who are prone to host this kind of systems, because otherwise could be really difficult to implement. Yep.
Thank you very much. So I actually also have a question, but I'll ask that later. So yeah, thank you very much. And then we head into our next presentation, which is by Ignacio Bugueño, Córdova. He is from the University of O'Higgins, and he is a civil electrical engineer specializing in artificial intelligence and communications. Telecommunications. He's held key roles in launching digital TV channels and radio stations, and has been a technological leader and advisor in various telecommunication projects. And he's about to arrive.
Okay, so thank you so much for being here today. Again, my name is Ignacio Bugueño. In English it's Bugueño, and today I'm going to talk about color event cameras for field robotics. But I need to, of course, to make a disclaimer. Just because I saw the previous talks of this week, I just make a little change on my presentation to just also talk about a project that we have right now in O'Higgins, and it's very related with all the things that we are working right now here with, of course, not only Rheinfall, also with the other universities. So the first things for me, and I take this as an inspiration from the previous days, is why are we here in this environment conference, right? Of course, we just want to have a very good overview of the state of research in several areas. The second one is to discuss hot topics and with very, very good conversations. But the third one is, of course, we need to make collaborations for all the threats that we have right now in the environment. And the best moment to have this collaboration is, of course, in networking. So I encourage yourself to take advantage of these moments, the coffee breaks, the lunch, the dinner, of course, to make collaborations. And yeah, that is why are we here. In my case, I am from an engineer field, so of course, we are not always so friendly. But this day I discovered that collaboration is so important, and that is the first message that I want to share with you. Well, the second one is my presentation. My name again is Ignacio. My background is an electrical engineer from University of Chile. After that, I did a quantum computing specialization at MIT. And finally, I had my Master of Science in AI and Robotics. I have several experience, not only in research and teaching. First affiliated with University of O'Higgins, UOH in Spanish. Also industry experience and affiliate to several institutions. And my areas are AI, computer science, 7-based vision that I'm going to talk about today, IoT, smart cities, several stuff related to technology. And yeah, I really work with several robots, now humanoids, Pepper. In fact, we, in 2017 and 2018, we participate in a robotics football World Cup in a league that is called SPL, Standard Platform League. And we sadly lose in the quarterfinals just because we played with a German university and we lost by a huge score. But yeah, at least we had a very beautiful photo, and again, working with several robots for different purposes. Yeah. Don't worry. Okay. Yes, with a glitch. Yeah. Okay. Thanks, Carly. So, what is my vision about technology? My vision is technology is a tool in the service of society. I know that everyone knows that we are right now in this evolution from, of course, to the 21st century, and we are living this fourth industrial revolution with digital transformation, AI, IoT, robotics, blockchain, even generative models. And why we are working with technology? Just because in not only today, also in the future, we want these smart cities and also smart industries. And I really love this animation just because we could see several services working at the same time, not only, for example, smart agriculture, even smart cities, and even Batman is there if you could see the light in some time of the animation. And why this is important, or what is the definition of a smart city, or maybe a smart industry? It's an intelligent ecosystem enabled by technologies with platforms and service for the benefit of society. And this is my goal also that I want to transfer to you today with my presentation. And these smart cities and smart industries are enabled thanks to cloud computing, AI, data science, 5G, 6G, technology as a tool, as an enable tool, right? So, okay. Also, I came from a very friendly university that is called Universidad O'Higgins. University of O'Higgins is in Chile. It's okay. Technical issues. Yeah. Don't worry. Thank you so much, Carly. So, Universidad O'Higgins is in Chile. Chile right now we are in summer there. So literally, I went to Germany from more than 30 degrees Celsius to -5 the other night. I literally suffered, but Germany is so beautiful also. And well, Chile is a narrow but a long country with a wide diversity of climate and weather, right? And literally, we are in the other side of the world. And Universidad O'Higgins was founded 10 years ago, yeah. And it's a university, of course, with advanced accreditation in undergraduate teaching, research, outreach, and also in other topics. Technically, I come from a robotics and intelligent system laboratory, where the director of that laboratory is Rodrigo Vertae. Rodrigo Vertae came to the first environmental conference 2 years ago. Of course, we have this vision, not only scientific and applied research, also technology transfer and dissemination, some topics that I'm going to talk about to you in a few minutes. And what is the relationship with Rheinfeld University? Technically, 3 years ago, Jan visited Chile for the first time. 2 years ago, a commission composed by Rodrigo and also Daniel Casagrande visited Rheinfeld for the first conference. And in this last year, in 2024, we had several activities between Rheinfeld and also Universidad O'Higgins, making some collaborations, even with the last conference that we had in Rancagua in the month of December, when Rolf and Walter enjoy a very good beer. I expected that in Rancagua. Also in dinner, and again, that is the reason why networking is so important. In fact, in the same dinner, but in another table, I was with Jan and Klein and other guys when they invited me to this conference, right? So for us, it's too special to be here, just because we are right now enhancing this collaboration with some topics, again, that I'm going to explain in a few minutes. So the first topic, or the first project that I want to talk about is a nice project that is called Transfer of 4.0 technologies for risk management in the cherry value chain in the O'Higgins region. And why is this so important? Just because right now Chile is consolidating his leadership around the world in the cherry market. And right now Chile has more than the 50% of world exports concentrating in Chilean cherries. So in this number, we just saw several, in this case tons are 1,000 kilos, several of amount of cherry exporting to the world. When the main country, in this case, that import this kind of cherry is China, right? Every year, for the China New Year, they buy a lot of cherry, and that's the reason why right now the Chilean product is so important, not only in the world, also for the Chilean market. So in that reason, it's important precision agriculture for efficiency and productivity, even for energy and fuel savings, reduction of chemical inputs, mitigate labor shortage, sustainability, and even the climate change adaptation that we have right now around the world, right? So we saw this and we say, okay, we know that right now Chile has a very good position in the world for the cherry production, but we really need to improve this. And how? Of course, integrating technologies. So what are some examples of smart technologies in agriculture? Of course, we have the environment, that is the farm and the field, and we try to integrate these sensors, smart technologies, not only with robots and all this kind of stuff, also with, for example, information communications technologies like LoRa, Narrowband IoT, and another kind of technologies. And also we are integrating right now imaging techniques, for example, like drones and satellite imagery to detect, for example, crop problems, such as pests or weather stress. Well, some technology tools in precision agriculture right now is GPS mapping, to just have a very good detail orchard monitoring, of course, optimizing planting. Robotics and automotive system. Right now we have this beautiful robot that is called Warhawk from ClearPath. It has a value of around $90,000, so it's a very huge one. And with this robot, of course, it has its own 4 wheels, and it's very good, not only for the field, even for the water. and help in this case to address labor shortage. Artificial intelligence and machine learning, in this case for automating the computer vision process, and in the future to have a very good estimations of the cherry orchards, and also integrating IoT and wireless sensor network when in this case, and we need to say this, we really thanks to Rheinfeld University for all their support and in integrating this kind of technology and all this knowledge to just have the current network that I'm going to show you in a few minutes. And again, computer vision, image analysis to detect pest, disease, and evaluate crop health. And lastly, satellite imagery. Well, field monitoring with artificial intelligence, we are working with hyperspectral imaging, IoT network in the fields, and lastly, LoRa technology and low-cost sensors. This is a hyperspectral sensor that is called PKL, and also I'm going to show you some image about it. And it's so interesting just because we extend the view in this case, or the range of our knowledge. It's not only RGB, of course, it could capture another frequency, and it's so important, it's so essential in agriculture. And right now we are working with this kind of technology that is called LoRa, for long-range technology, that allow us to have, for example, one gateway, one antenna, and this antenna could cover from 6 kilometers until 10 kilometers. So literally we just put one antenna, and it has a coverage like around 10 kilometers with several sensors working right now. Also, we have a very good service that is working right now that is called the cherry counting service through artificial intelligence. In fact, this was the Master of Science topic of one colleague and friend that is called Luis Cosio Montefinale, with a database and method that was published at IEEE. When in this case, these videos are from the people that are working, in this case, in the fields. And they literally took, in this case, I don't have my smartphone here, but they took their smartphone and start to just, of course, with a slow speed to take image of the cherry orchard, and then they send these videos to a cloud service, and in the cloud service, this is processing using YOLO networks and other kind of networks. And if you could see, the cherry is a very, very small fruit. And then, for example, you could see that there is the bounding box of the cherry, but literally it's too small. And the work that in this case, Luis, and right now is a service being created to University of Higgins did, and it was so challenging, just because it's not detecting, for example, a dog, or detecting, I don't know, a building. It's detecting this small fruit and allow us to give this as a service for specific farmers, and of course to have a better understanding of the volume estimation. Also, hyperspectral imaging, when, as I told you before, we have that in traditional cameras, RGB, they work in a specific wavelength, but in this case, hyperspectral cameras, they are not only in an extended wavelength, also in a continuous range, right? And in this case, these different plots represent, for example, the flower, the leaf of the flower, and also this bottom part of the flower. So literally, with this kind of technology, we could identify, thanks to this extended and continuous wavelength, different important features of, in this case, for example, for the cherry orchards. Well, some scope of the devices, as I told you before, we also integrating LoRa network communication. LoRa is a long-range network with several sensors, and with this kind of architecture, in this moment we have 5 gateways. Gateways is an antenna or base station. They are in Rancagua, also in Requinoa, Peumo, Graneros, and Rengo, and right now we are extending to 3 more antennas. In fact, when I come back to Chile in March, I need to deploy those antennas with so much code. And also, with these antennas, we send this information to a TTN server that is called the Things Network server. It's an international server. And then we could just extract the information and, of course, report this as a dashboard, right? So, for example, this is right now the Things Network coverage. if you could see right now, there are several in Europe, and if you want to go, to do a zoom, you are going to see also that we have several of this network in Germany, but in Chile, it's this one. And if you just give me a moment, I'm going to show this in real time. Going to make a zoom, make a zoom, make a zoom. This is Chile, this is Santiago, San Fernando, and we have this one. Oh no, we have a we have a problem. Yeah, maybe this one is going to work, right? Yeah, for example, we have there one gateway working right now, but if finally you could see, compared to the rest of the world, we have just a few antennas compared, of course, with the current state of the art. And of course, our goal is to just not only enhance the network, that it could be a very good example for other countries. And yeah, also with these kind of technologies, right now we could have a very good idea about the call hours in a field. The call hours is not only important for the instant moment, also it's important as accumulation, right? Because the cherry orchard suffer with the accumulation of call hours. So this is, for example, from May and June from 2023, and also the call hour maps of the Graneros field. And this information is so valuable for the farmers. And when the farmers see that, okay, we integrate robots, we integrate LoRa sensor, we integrate this antenna, oh wow, they're not going to replace us. This is, of course, a support tool to just enhance our production and knowledge. So what we are developing right now with this project, relationship with producers and exporters, productive areas, strategic alliance, and also this LoRa sensor network. So what problems opportunity we have right now? Connectivity in rural areas. That is the reason why we are developing this own network that is called LoRa. Lack of technological adoption, not only with farmers in the country, and of course the need to maintain this sensor and equipment in the time. Opportunities, LoRaWAN network expansion. We are working right now in this. In fact, between January 2025 and March 2025, we're going to just deploy more than 300 new sensors. This was only in one specific row of a field 3 weeks ago in Rengo, and the regional government is so excited about this project, and they funded us with, of course, with new fundings, and they allow us to just vote new sensors and of course extend this network. And also we are not only working to enhance this network, also we are working with drones as a monitoring service. It's, of course, it's a drone in the top of a field. And in this case, you could see the several cherry orchards, only cherry orchards in Rengo. Right, it was in Rengo. And yeah, of course, it's going to be too difficult to detect cherry, but at least we could just have a very good idea of the status of the orchard. And then a video, of course, I could share with you. So this is, for example, the cherry orchard in May and June when it starts to just flourish, right? And then we are using, for example, this hyperspectral sensor to detect the different wavelengths, and with that detect, for example, the leaf, the fruit, and all these kind of things. And again, also we need to measure the size of the cherry. Again, just because we are right now leading this market in the world, concentrating more than 50%, and we need, of course, to improve not only the quality of the cherry, even the production of the cherry. Okay, in the last 5 minutes, sorry for the extension, I just want to talk about some topic that we are working right now, that is called exploiting visual information in field robotics using color even camera. I don't know if you know about color even cameras or even cameras, but I'm going to give you a brief introduction. We know that in robotics and computer vision, we have several applications, drones, real-time post-estimation, file robotics, real-time chair detection, human-to-robot interaction. But the question is everything solved in robotic vision for agriculture? And the answer is no. For example, in robotic vision, we have latency for high-speed applications or environments, motion blur, dynamic range. We take, for example, a photo of a beautiful sunset, and maybe the camera is going to fail. So traditional cameras have this kind of problems. And there is a new sensor inspired from biology that are called even cameras that don't suffer from these problems. So what is an even-based camera? It's a novel sensor that measures asynchronous pixel intensity change in a scene, only change, right? So if we, for example, have a standard camera and we are tracking or recording, this dot around this circle, standard camera are going to produce with a fixed time, always an image, always an image. It doesn't care if the dot is static. No, standard cameras are going to always take pictures. But in this case, even base camera, also called dynamic vision sensor, only detect the change in the scenes, and if there is not any kind of motion in the scene, it's going to be quiet, right? So technically, this sensor generates a tuple that is called event, and it's composed by position, time, and polarity. Polarity is the binary chain of intensity. This camera doesn't have blur motion. They work with a very low latency and also with a high dynamic range. So this is, for example, an even-based camera. And even-based cameras are interesting just because they're also called neuromorphic sensors, and they take inspiration from how our brain works when we just have two kind of visual pathway, the dorsal and the ventral. We have the sustained pathway, the ventral, that only focus on the details. And the main problem with this visual pathway is that it's slow. It's the color image, for example, right? If you, for example, want to move very, very, with a very high speed your head, you are going to see everything with a blur motion. But in this case, the dorsal visual pathway concentrates in the wear, and this is the motion, right? And this camera only wants to capture the motion. So this takes inspiration, these implementations, from the ganglion cell. I'm not going to talk about this with a more detail, but it's interesting, the inspiration from these cameras. And technically, again, they generate this information that is the pixel position, the time, and only the binary chain intensity. Only this is a sign of the brightness change. We have, for example, a brightness increase or maybe a brightness decrease. Only that. So if we see an example of a traditional camera with a even-based camera, we know that, for example, depending of several parameters, like for example the exposure and all this kind of stuff, a traditional camera could have, in this case for high-speed applications, a slow motion, but even-based camera only focus on the motion, and they generate, in this case, a continuous motion, right? A continuous information. So it's perfect if we just have, for example, high-speed environments, for example, a drone in the cherry orchard or something like that, and it's going to take that information. So if we see another examples, in this case we have, for example, some guy smiling. Frame-based camera are always going to take information from him. But for example, an even-based camera going only take information or generating information when we just see motion in the scene. This is very interesting. This is, for example, only blink, right? And you could see here the blink of the eye. And this is what these cameras are generating. So what triggers an event? In this case, moving edge, for example, a moving object in the scene, but also if we have a moving camera, as I'm going to show you in a few minutes. Some applications, this is more related to robotics, image reconstruction, post-estimation, visual inertia odometry, and also right now we are working in several topics in University of O'Higgins, for example, reconstruction from events, for example, to an image. This is the original image. These are the events. And this is, for example, our reconstructed frame. They are very, very similar. And also another topic, for example, visual surveying for human robot navigation. And also, for example, a data set of moving objects to trying to catch there in the air. And what about color event cameras? We know that color information is essential for robot vision. You could see several surveys about it. But we have a problem, right? Just because almost all event cameras work in grayscale. And I'm going to show you an example right now. Sadly, I couldn't bring an event camera with me just because it costs 5,000 euros. And I don't think that Rodrigo allowed me to bring it by the plane. But we have a demonstration that I'm going to explain in a few minutes. And this is, for example, a color event camera, event camera. And if you could see, this is the grayscale image, and this is, for example, the events, right? So, for example, if I am just with no motion, it doesn't generate any kind of information. But if I start to move, they, of course, generate this that is called events. In fact, if I start to move, I'm in there. And if you want to move your hand or wherever you want, you're going to see that it's working. The resolution in this case is too bad, just because even cameras work with like 100 per 100% resolution, but at least it's a very good approximation. And right now it's only working with my webcam, right? And you can see we have the grayscale and also the events. And give me a second. I'm going to take a moment to make another day. So almost all event camera works in grayscale. So 2 years ago, in collaboration with University of Southern Denmark, we proposed to, in this case, elaborate our own color event camera, but an emulator color event camera, based on some, of course, theoretical fundamentals from TU Berlin, and also from only one event-based camera that right now, sadly, is not available in market. So we think that our emulator is going to be interesting. So our proposal in this case is, of course, to take for this emulator RGB videos and extract meaningful information using emulator color events. And this is integrated right now in ROS, and we could just use this emulator, for example, in this kind of robot that is called Warhawk. And technically, we have the RGB frame. We made an interpolation between the frame to have a very good timestamp resolution. Then we make the splitting RGB channel. We calculate the luminance intensity log, and finally we could just generate the color events. So the demonstration, this one, for example, we take this video from a visiting cherry field in O'Higgins. And then we could just make a video with the robot, and we could just generate this color event camera with this, for example, blue GGR pattern, right? And for example, I suppose that it's working right now. In this case, we develop a new emulator, again, only from webcam. We technically reduce the cost of like 5,000 euros to only the price of the webcam to have, again, it's an emulation. It's not exactly as the original sensor, but we think that it could reduce the gap between the people that want to work with this camera, and of course, they could just try their methods. So again, if I move here, you can see that it is working. And also, if we just want, we could just combine the information from the RGB camera and also with event camera, and we think that they're going to enhance the performance. So just for the time, I know that I extended a lot, sorry for that. We right now, we work in progress that we are integrating this kind of camera and field robotics. No one is doing this right now, and we think that it's going to improve detection, tracking, volume estimation, and of course, this is a tool, but a tool for the service, in this case for smart farming, and not only in Chile, also in other parts of the world. So, also presentation, thank you so much for your time.
Thank you for the interesting talk. We have no time for questions technically, but does anyone have a super urgent one? Okay. So we'll do this in the next coffee break. The next speaker is Jan Sonntag. Jan Sonntag is a researcher here at Hochschule Rhein-Waal. He's also a very integral part of the LaTeNet project. And he will talk about drones, about mines, and about sensors in mines. He does a lot with LoRaWAN techniques, Internet of Things, and it's all pretty cool. I think there's a lot of applications of what he's doing with a lot of what some other people are doing, and therefore, yeah.
Thank you very much. Quick check if it works. Seems good. Fortunately, I got a bit sick, so you can still hear it a bit in my voice. Harley, we need more volume. Perfect. But that's maybe a bit too much. So today I want to present the project I'm currently working in. It's called DITER. The lead partner has a tendency to use classical German names to name their projects after. But as you can already guess from the name, yes, we develop an automated monitoring network. And just in general, this is an Earth observation and IoT lab project, and the idea is we develop a handbook how to basically place these automated network, how to build them up, so there's documentation on our wiki available. But how did I get there, basically? It's a bit, we go a bit into the past, and we see everything started here. I didn't knew it back then. I was in the Amazon forest. Eric brought us there, and I was placing LoRaWAN infrastructure in the Amazon forest. You can see me there in the middle of the bushes, and this is what I presented 2 years ago at the first environmental conference, and it was basically our idea how to basically have LoRaWAN sensors and use edge computing to save the data locally and then make it available on high-speed servers elsewhere. And this is basically also what I'm doing in DITER. Here you see me 2 years, or this was I think a photo 3 years ago in the Amazon forest, and this we took last year, where we now develop sensors for underground mines. Just like some quick details about the project. So the lead partner is the Ruhr-Universität Bochum. We already had 2 people here from the hydrology department already. Then there's us, the University of Stuttgart, and a local company from Dortmund, which develops basically the online dashboard and yeah, more details about that later. It's BMBF funded, and it will go until the end of 2026. Like, the general idea of the project is to make a hardware but also software-based monitoring, which will in the end, should be like a digital twin. So everything that happens basically in the mine can also be simulated very accurately via software, so we need less sensors basically in the mine in the end. But the general objective, what are we doing with the data? Of course, we have hundreds, maybe even thousands of these mines that are unused, closed for basically already decades, but they're still there. How can we use them, or should we protect them somehow? Are there an influence on the people living around them, basically, that maybe don't even know that they are there? So we have to also make a scenario analysis in the sense, how can we exploit them, basically? Not in a bad way, but in a good way. For example, might they be useful for geothermic energy? We have our work package is work package 1. because we work basically in the establishment of the automated monitoring network. This has 3 parts to it, and this is very applicable to all sorts of different projects that are regarding sensors. So in general, we need data transmission, how to get data from A to B. We need our sensors. What do we want to sense? For example, temperature, humidity, electric conductivity. But also, what is the software infrastructure behind it? So how do we want to save the data? This, as you can see, is applicable to all sorts of different projects, not just this. This is just a bit more special because it's in a mine. So generally, what do we need? We need communication outside and inside of the tunnel in our mine. We need some failure safety. Of course, we don't want to lose any data just because maybe the internet has broken down or anything. So we want to avoid data loss, but we also want to maybe use this information for like safety of the workers inside the mine. And what do we need, or what can we do inside and outside of the mine? There are different technologies that we are using. A lot of people heard about Starlink. Maybe the mine is a bit more remote. So there is maybe no other internet connection available. Maybe we can use Starlink for that. But also inside the mine, do we want to lay cables everywhere? Do we maybe want wireless transmission? Maybe you know more, they use different frequencies of radio waves, so what can we do best there? And it's a very new environment for us as well, so we also did some tests regarding that. But then also, what do we want to measure inside the mine? What is important for the city, which is the official owner of the mine, but also what is important scientifically? What values, which parameters do we actually need to, which parameters do we actually need to measure? So for us, our main focus is the mine water. This mine is almost fully flooded until the top. Only the top levels are accessible. The last 800 meters, just water. So we want to know what are the water levels. Are the water levels changing? The electric conductivity, can we maybe use it as a tracer for the water, where the water is coming from? And also the temperature of the water. For example, I already mentioned it, geothermal energy. Because the water, I can already tell you, is quite nicely warm, 27 degrees all year round so far. So is there a change over the year? There's also a bit of a challenge. I already said it's 800 meters of water. Is it always the same? Probably not. They already did some first tests, of course. So we also need to see what are the changes basically in this 800 meter water column over the year. Maybe we can already backtrace basically what is happening in 2 months at our level that we are currently measuring at basically the water that is coming out of the mine and 800 meters that is down in the mine. But just in general, the expansion of the network should be possible. It should be easy to add new sensors. Maybe we notice, we need sensor B now. Let's just add it. And also the weather is quite a nice term. We think about the weather outside, but there's also weather inside the mine, should of course be recorded. And then, the software infrastructure, I think that's the most boring part about this project so far. Like, okay, the data needs to be accessible outside the mine, basically. So we also want to be able to support many different data protocols that the sensors might use, and we want to make it as accessible as possible for the other partners in the project. So, like the technical term, we want to have an API. Like every program should be programmatically be able to access the data. And there we go, we are in the gallery. It's called Neuhoffnungsstollen, very nice German name, but it's basically called New Hope, if you translate it into English. They mined lots of different stuff there. It was everything from iron, lead, copper, just everything but coal, basically. We have some nice photos. There was a student who did a small photography work for his design study program. His name is Alexei Kandinov. If you see any very, very nice pictures in this presentation, they're from him. Here we just come outside of the mine, and then we go inside, basically. What are we working with? This is a 600 meter long gallery, but there are basically more than 20 levels to this. We stay mainly in this one. It's accessible on street level, and then we have multiple shafts, basically. So we have the entrance, then after roughly 350 meters, we have shaft 1 and 2, and at 600 meters, shaft number 3. The only shafts that were ever operational are shafts 3 and 2. 1 they closed after 30 meters because there was a big rock. But then we go inside. It's a bit darker there. We need helmets, we need helm lights. We turn it on, we check that everything is basically with us that we need. You don't want to walk back the 600 meters all over again. It's a bit darker. We need to walk all the way to the back. There are paths that you maybe want to take to see some nice relics of the old times. This mine was closed in the 40s after the Second World War. There are also other paths you shouldn't go into, just to say that, but they are luckily closed off. And then we reach shaft 3, where we do most of our research work and deploy most of the sensors. Here is Henrik, he's the technician of the project, just deploying a EC station, as we call it. But the most important thing, how do we get data throughout the whole mine? It's 600 meters, and as I said, there are hundreds of these mines available. We can't just lay a 3,000 euro cable from the front to the back, because that would not be applicable. We couldn't deploy this in other mines. We need to make it as cheap as possible, basically. So what I did, we already have experience with basically wireless link bridges. So I took 3 that are already new with different frequencies. We tried 2.4 gigahertz and 5 gigahertz with also different antenna characteristics. What you can basically see here is this one here, the 5 gigahertz light beam AC by Ubiquiti, is a bit more focused. The Loco 5 AC is a bit more broad, so it has a wider spectrum, as you can imagine. And then I also tested one 2.4 gigahertz wireless bridge, which is a similar characteristic to the Loco, basically. Also very wide, not that focused beam. And what I saw here, you can see, or this is actually the final thing that we used. We did 5 to 6 measurements from the front, and then at different distances. And we could see actually that the signal strength is almost linearly taking down. The gallery is almost straight, except here we have a slight bend and curve to it. But then we thought, okay, the signal strength is not really that different, but we could see that the 5 gigahertz light beam 5 FC, which is very pointy, has the best one. So we already thought going for it, and we just looked at the capacity, how much data can we actually get over this link, like an Ethernet cable, for example, how much data can we pass per second, and we could see this one is an Mbit, so how much megabits per second, and then we could see, okay, the 2.4 gigahertz dropped down very, at a 5 gigahertz Loco, which is very broad, dropped down very significantly, especially in the end when there was not a very pointy shaft anymore, a gallery anymore, and that the 2.4 gigahertz was always lower and dropped even more, basically. So where we are going for is in the end with this very pointy 5 gigahertz antenna. And then, okay, but how do we connect our sensors? Here's just 2 examples. We tried our Bluetooth Low Energy and also LoRaWAN. And we could see here Bluetooth Low Energy, it dropped down very fast, and already after from 0 to 90 meters still quite far, but we are working with a 700 meter shaft. It was already breaking down, there was no connection possible anymore. So we figured Bluetooth Low Energy might work for close by sensors, but it's basically useless for us. LoRaWAN on the other hand, as you can see here, we are not working with 90 meters, but we are actually working with the full 600 meters of the gallery that we are working in. And still, there was always a connection possible. The signal strength is not great, I have to say that. Might be improvable, but we were working also with not the best antenna, I have to say. And still, we were able to get a good connection, a steady connection all the way through the gallery. So, in the end, we were now using mostly LoRaWAN technology, which is working on also, that's what we noticed, on a lower frequency and had the best results. Here's where we're doing all the water experiments, let's call them. This is shaft 3 on a bit one lower level. Here we walk actually in the water that gets outside, that goes or comes up through the shaft and then flows to a nearby river. What are we doing here? We developed an EC measuring station. We wanted to measure the conductivity of the water, the temperature, and the level of the water. The problem is there are some smaller and larger pieces of iron hydroxide in the water, and you can already see it a bit here. It looks muddy. It's not mud, it's really just iron hydroxide. And a little arsenic, but we don't care about that right now. As long as you don't bath in it, they said it's fine, so I just believe them. This is how an electric conductivity sensor looked after like only a week. It is unusable, like already after 1 or 2 measurements, there was some sediments on the sensor, unusable data basically. So we thought, hey, how can we solve this? Easy, we just put it quickly into the water, take our measurement, take it out again. That made it even worse. So it dried up immediately, every little particle that was on there. So what we came up with, now we clean our sensor after every measurement. It's in an automatic fashion. The mechanics actually worked already for more than 35,000 measurements. So we are quite sure that this will work in the long term. And what we do is we use hydrogen chloride. Yeah, hydrochloric acid, that's it. In Germany we just call it Salzsäure, it's so different. So basically now what we are doing is we are putting the sensor in. We used off-the-shelf parts, actually very close to a 3D printer. Just put it in the water, do our measurement, and then take it out, get in the bucket, put the sensor in the bucket, and it gets basically cleaned chemically, which is also the way that the manufacturer of the sensor says this is how you clean it properly. So now we know with this, like 1 bucket of the acid, 2 months of measuring, then you just need to change out the acid, that's it. And what we also get out of it is a very precise measurement of the water level through it, because we sense basically like a 3D printer senses its bed, where's the water level. There are also other ways of doing the water level, like ultrasound, radar, laser, or pressure. Unfortunately, especially ultrasound, radar, and laser, at least with commercial solutions right now available, they're just not precise enough for scientific use. For general use, they might be good enough. So currently we are going for pressure sensors, and we did the first test. We currently have 2 deployed. We want to deploy a 3rd one. But this is an issue we didn't see coming. There is CO2 rising inside the water. It's literally bubbles of CO2, and they capture inside the pressure sensor and then completely make the results unusable. And the solution is you just hang it upside down. Then there is no CO2 catchments anymore, and the pressure sensor is working flawlessly. And this is also what we used before in a groundwater measuring concept together with Linek, the local company taking care of all the water bodies here in the region. So we had already some experience with it, and it was very quick for us to deploy it. As a software infrastructure, in this case, because we are working in a very special environment, let's say, the software is very closely related to the hardware that we are using. And as we are using edge computing, we basically have a server inside the mine, which is just a Raspberry Pi. But basically, we don't need an internet connection for the whole system to work and to record data. Luckily, we have power available there all day around, in theory. So what is currently happening is, just to quickly go through it, we have a sensor which uses LoRa or LoRaWAN to send to a local gateway, which is running all the hardware and software to basically make the software sensor connection possible. Then this sends it to the local server. The server basically saves it, and then through the wireless link that I explained before, sending it to the router. And only the router in the front, in the entrance of the mine, has the connection to the cloud server. So as long as there's internet, this database and this database are the same. So if I want to access a lot of data, then I will just connect to the cloud server and have a very fast and responsive connection to it, basically, and retrieve all the data at once, because this connection currently from router to the cloud is otherwise very slow. I can access it. I could go to my laptop and access all of these hardware right now, but it's just too slow for huge amounts of data. Yeah, and we divided it This hardware is basically in the back at shaft 3 because that is where we have all the data. And then we just have one small data node which mainly includes the router that makes the outside connection possible. And what are we seeing now? Like some first results that we have is, this is for example the level of shaft number 3, and we see daily fluctuations and like a bit of noise as well. And we were asking ourselves, are there really minimal daily fluctuations? Because we are talking about a couple millimeters here per day. Does that make sense? If so, why? I'm not a hydrologist, so I can't really answer it right now. If not, are maybe our like our measurement sensors, are these maybe on fault? And what we now did, because now we have a bit more data, we actually have a pressure sensor and we have our EC measuring stand. Both have completely different ways of measuring the water level. And now this can be done live actually. We have it in a browser. We combine these two. The yellow one is our EC meter, which has a bit better accuracy or at least resolution. And the pressure sensor, and we can see they follow the same curve, at least roughly. Sometimes there's a couple millimeters or micrometers difference, but that's fine. So we say, yes, there are very likely daily fluctuations because two different principles of measuring show it, but we still don't know why. So this is what we need to find out. What we currently want to investigate is, these were suggestions by our partners. We want to actually see the barometric pressure changes inside the mine, because actually they had experienced that it's pushing down the water or let it rise a bit more. Or it seems to be, at least that's what they told me, in a recent paper they even showed that these small changes, you can see here was a bigger change, but normally it's really a couple millimeters. It could be tides actually. No idea, we still have to prove that. More on that in 2 years hopefully, in the next conference. But there's still a lot to do. We now want to start with the spectral analysis of the water by deploying a spectrometer, possibly at -40 meters. It will be submerged in the water. We will now start working on the CO2 fluxes in the tunnel, measuring WERS to get basically the output of the mine water, so we can actually quantify that. Right now, there was one measurement taken at one point in time. It was 37 liters or 44. But we don't know if there's a change over the course of the year. We want to install rain collectors, measure the airflow basically, and also maybe in the end want to do a crack monitoring for security reasons if there are cracks in the mine, in the walls that basically drift apart, which would or could conclude that they maybe are short before collapsing or there are changes in the geology. Thank you for listening, and if there are any questions, just let me know.
I think that was, yeah.
Thanks, Jan, for the presentation. Could you go back to the dial fluctuation of water, please? Yes. That has been measured. You're measuring at the surface level, right? We see this dial fluctuation in stream water monitoring. It's very. Some people say that evapotranspiration, so plants really, and soil evaporation actually, and make that really different. I would suggest if you could see the time, yeah, that you have it. So if you have it, let's say the maximum, it's at the maximum or the lowest during the day is at maximum sunlight, yeah, or if there is some shift, that could be one reason. But the other reason, it's also thermic expansion. So water with some degrees can have a bigger volume or less. Yes?
So actually we monitor the temperature as well. I just don't show it here. At least the temperature of the water, which we have pretty accurately, it doesn't change. Like, it is within the spec of the thermometer that we are using, and it's like 27.1, and then maybe 27.11 or something. That is the change that we are working with. And what I could see is like there is basically a low at night, then a rise to a high point shortly before like 12 o'clock. Then it goes down again, and then one up in the evening, and then it's basically back to the night level, I would say. I don't know. We don't have any plants. We don't have any sun, so no idea what it can be. But we have fungi. Yeah, we will see tomorrow. So.
In the end, if you see out here, you see grass, and grass also sucks up water. And then in the, I don't know how far is the soil from there.
Around 80 meters, but that's above us.
Yeah.
A couple hundred meters, I would say.
There might be just as temperature. Yeah, you could. It's an idea. I'm not saying it is that, but yes, we will see tomorrow for sure. Thanks.
So maybe
we have two measurements. One is the pressure. This is the green line. This sensors in the water, and the yellow one is our EC measuring station, which really just touches the water level.
but it's still on the surface.
Yes.
It's not in the depth or near the walls. So maybe there's still some change.
It's like kinda near the walls, like the where we measure it in the shaft. It's like a 2.5 meter like tunnel basically where the water is flowing through. That's where we are measuring. But we will now start also measuring at another location, hopefully, and by the end of this year, which is like 500 to 600 meters down the line, and then we will see if there is also the same fluctuation basically.
Because it's a very deep shaft.
Yes, it's very
deep. So there must be some different temperature measurements.
That is why we need the depth measurement basically. Like this water column, we want to profile it basically, like at least once or twice a month, not live, but then I hope we get more.
The theory from behind the thermal fluctuations might still be correct if we have more measurements in it, but for the whole profile.
Yeah. Later, more later, as I said in the next conference.
The money. Thank you, Jan, for your talk. It's amazing the improvement from last time we talked about this 2 years ago and what you have now. It's pretty amazing. Just two quick questions. Regarding the geology of the tunnel, are you planning to try I suppose, in different geological settings, different tunnels in different geological settings? Because maybe that the signal strength may vary depending on, let's say, the amount of iron in the rocks or whatever. And for us in a volcanic setting, like in Tenerife, the crack sensor, it's really useful. We don't have really big faults, but the cracking is a really nice information for tracking geological activity. So, you know.
So this project would be only in this gallery so far. Maybe we will try to deploy it in a second one, but it's in the same area. Like it's not far away, but I mean, at least for the tunnel testing, like the infrastructure, I can just pack it and then come to you. I think that would be the best. And but the crack monitoring, I will talk maybe a bit later in the second presentation with Farley about it. But I think, yeah, we saw there are many different applications where it's basically needed.
Okay, I think that was all the questions right now. Yep. Then thank you very much. And we will have a short coffee break. We'll see each other again at 12:35. Okay. Okay, let's get back to our seats, please. Okay, we'll have some food later, but for now we will have our next presentation. Soonish. Okay. I think we're hearing the construction noises from outside. Okay, I think the shorter the coffee break, the longer it takes to get back into it. So I'll try to make us have a better lunch break so that we all have some time to talk between each other. Okay, our next speaker is going to be Pedro Hervé. He is from the University of Magallanes, and he's an environmental scientist specializing in hydrology, ecohydrology, and biogeochemistry, with expertise in water resources and quality in forests and mined areas. So he's going to be talking a bit about that.
Thanks, Magdalena. Well, the presentation today is part of a project that I'm working on. Yeah, it's using. Thank you. It's using specific conductivity to understand soil water dynamics and inform the land manager or doing some land management to improve, or again, I'm not going, you will see in the presentation. But now I'm in semi-arid ecosystems. This beautiful scenery that you see there receives around 200 millimeters per year. Yeah, it's highly windy, so you have wind almost every day, and high wind almost every day as well. So evapotranspiration and water is an even more precious good, yeah, for the ecosystem. I mainly work describing hydrological processes, yeah? And as a good hydrologist, we always avoid getting into the soil, because soil, it's a black box. It's sometimes hard to measure, and when you do a measurement, you need to destroy it in order to take your measurements. So again, it's not very feasible. But in this sense, tracers, specific conductivity, other ions, stable isotopes, can be used to describe these processes. Yeah? By specific conductivity, I am related to electric conductivity, already corrected by temperature. Usually this is done at 20 degrees or at 25 degrees. Yeah? And well, with the use of tracers, again, you need to interpret this data, these lines, these values. So you become, I would say, an analog intelligent pointing on that on that direction. Maybe AI has something to do or will have to say something in the future. Hopefully in the near future, and please, you're welcome to collaborate. Yeah? So basically, everybody here has been under the rain, I would presume. When it rains, there is water, and water infiltrates in soil. The water that reaches the soil, yeah? Not the water that interacts first with the vegetation. And then you have another process that is the percolation. So when it goes from one layer of the soil to the next one, yeah? Here I put arrows pointing downwards, but also percolation, it's water that goes to somewhere else. So you can also have lateral percolation, yeah? In this post-mining environments, you really need to reduce infiltration to control the amount of percolation, because percolation comes with things you don't want to treat, or you want to avoid. In the field, we can do these sort of experiments and understand how infiltration actually is working using blue dye. It's a very simple experiment, and it can be super insightful in the sense of how deep water will go after a simulated rain, or how wide will it go on one place, will it go all even downwards, again. And what you see here, it's what we call preferential flow. So flow is not going even from top to down, but using specific pathways. Roots, wormholes, other insects that make these burrows and so on, water gets there, and that makes infiltration look like this. This is what is most commonly seen in the environment without alteration. And if you have infiltration really going downwards, super even, then I would say there is something going on there. So infiltration can also be used as like the body temperature. Oh, I'm sick. What's your temperature? 39. Of course, you're sick. What do you have? We don't know, but you are feeling terrible. Infiltration in this sense can also be used like that. So for me, infiltration and understanding how infiltration happens, it's paramount. And well, the conflict. Yeah, there's always a conflict. We try to solve solutions, and of course we will find more problems than solutions, but we will get there eventually. In there you have a guanaco, the one with the long neck, yeah, and a sheep. So sheep are farmed extensively in Magallanes, yeah, extensively because the area where they grow sheep, or it's sometimes, let's say, 40,000 hectares for one producer. So really extensively, yeah. And there's the usual, in the end, fight for food, because in an ecosystem where you receive 200 milliliters of water, grass growth or plant growth or vegetation growth is very limited, first to water availability, but then to temperature. Yeah. Very deep in the south where I live, temperature in summer, sometimes now with climate change we have 27 degrees, but it's really rare. But on average it's 17 degrees. Yeah, so that's summer for me. So this is not summer, but getting there. Huh? And of course, guanacos have a bit wide feet, while sheep have other very pointy feet and so on. And in the last 150 years, sheep production has been very, very important for the region. Yeah, this, the sheep or the livestock producing activities has also produced some landscape changes. Yeah, before the rangeland, I prefer to use the word rangeland rather than grassland, where everybody thinks it's grass. Rangeland was cleared. Yeah, and here you see some stripes of bushes, and then some stripes that they were cleared early in the 1900s. Yeah. This is to promote grasses for the sheep can go and again grow. Then we have parts that are or have been heavily grazed that you see here on A, yeah. While if you compare A and B, that's a heavily grazed and just a grazed piece of land, you see differences. Yeah, differences are very clear. This I didn't make this with the AI. I was just standing and took the picture, and that's the difference you have on a fence on one side or the other. So again, infiltration of water is super important because without water, vegetation just doesn't grow. Yeah, the same as carbon fixation, and the same as biogeochemical cycles. They need water. Without water, it's all empty. Yeah? So when you have these heavily grazed areas, they are more prone to be replaced by another kind of vegetation. Yeah? These are locally called murtillar. Murtillar, it's an ensemble of dwarf heath shrubs. They are 5 centimeters at the most, but they expand like islands, like lichens. Yeah, it's more or less the same. And due to erosion, mostly done by the wind and water, of course, then you have these little islands that are, again, rocks or sands or small pebbles and so on. And, of course, nobody wants this because it produces almost no grass for sheep or for guanacos. Yeah? And currently this kind of vegetation is expanding each time it's faster due to the degradation of the rangeland. Yeah? So after 150 years of sheep production, and of course not the most friendlier ways, you have a heavily grazed rangeland that is lowering its productivity, being replaced by this. So again, we have a big issue. So when I first arrived to university, I decided to say, okay, let's measure infiltration in each of these different areas. And we found that some of the soil presented water repellency, since it's super dry and the carbon content is close to 10–15%. Dry soils are hydrophobic, so it rains, but the water stays there on the surface, and then the wind comes and takes it away. So you have a 10-millimeter rain, everybody's super happy, but how much of that rain went in? Nobody knows. Yeah, and also it's very important the infiltration rates can give you insights on the field saturated hydraulic conductivity that provides some idea on how water moves or how wet needs the soil to be so the water can move downwards. Because if the water is only penetrating the 5 centimeters, the 5 top centimeters, then you have a problem. Soil is a big storage of water in the end, yeah, along all the biochemical processes that are involved for nutrients and so on. Yeah, these infiltration measurements are the simplest thing to do. Yeah, so you pour water there and you see when it goes down. Basically, you take a measurement of the time and then you pour again the same volume, and you do that until you have 3 or 4 measurements that are they take more or less that time, the same time, sorry. Well, sensor technology there, it would be a blast, but okay, I'll keep going. Yeah, so basically when you have a fluffy soil with low density, water can go there and really go deep. However, if you have a heavily compacted soil, pores are really small and water circulation in the soil is not very good and prevents lower soil strata to be recharged with water. Also, with the infiltration measurements, we can gain some insight on the soil moisture retention curves. Yeah, I don't know how many of you are soil-related scientists. They can raise or understand soil. 1, 2, 3, 4, 5. Yeah. Okay. Well, it works. Yeah. So this is the permanent wilting point. So all water that reaches all this water, soil has water, but it's not available for plants. So plants are dying basically. This point here, the field capacity, is the maximum amount of water that can be stored by the soil. Yeah. Water and air. If you have a flooded soil, that also is not good. Yeah. So this is the amount of water, yeah, that plants can use. Of course, different soils have different, so again, we are adding more complex things to something that we started thinking, okay, it's super easy. Huh? And then, sorry. Yeah. Then if you measure a tracer constantly in precipitation and in the soil, you can actually solve this equation. I think most of you are engineers, yes, or a mathematical background, harder or bigger mathematical background than mine. So with this, you can actually measure how much of the precipitation water is being on where you are doing the constant measurements. Back in the 2000 or 1990s, constant measurements were, at least in Chile, simply not available. You have one daily measurement and probably you would have to send somebody or you have to go and measure it yourself. Nowadays, with sensors and of course sensing technologies, you can do these measurements of some of these tracers, in this case electric conductivity or specific conductivity. You can measure it at a rate of, in my case, 15 minutes. Yeah? Over 1 month, 2 months, 1 year, 2 years, and so on. So you can have a really big time series to do this. Yeah? It's very important to have here the precipitation concentration of your tracer. Again, electric conductivity, we can use it as a tracer. It has a semi-conservative behavior. It's not perfect, of course, but it gets us, leaves to understand us something. Yeah? All water concentration, yeah, in soil, so it's water that has arrived there and has already been chemically reacting, so it gets more compounds. Yeah, and the soil water content, that is something we should know. And of course, you have an unknown mixture of these two, and you have a value of electric conductivity that is a mixture, an unknown mixture. But solving this equation, you can have this, the amount of precipitation water that you can have in your soil. Yeah. So the research questions. Yeah, we already the infiltration rates, but can we use soil specific conductivity as a tracer for water infiltration in soils? Is there a difference between these different land covers? And for me, what most important, can we identify types of infiltration? Preferential flow or this very low infiltration using specific conductivity? Yeah, some information I forgot to mention is that in Chile, yeah, well, most of you know where Chile is. They're really, I think we're the longest country in the world, or thinnest, that also can be. So steppe ecosystems or rangelands are 90% of all the Chilean rangeland ecosystems are in the region. So again, it's important not only for sheep production, but also to understand how the steppe ecosystem is behaving. And again, climate change. We still, in the upper part of Chile, the north, so the Norte Grande, central north, center, and south central Chile, we know with certain account that what will happen with the climate change. However, in the austral part, there are some suspicions that something is going to happen, but we just don't have just the westerlies, but we have Antarctica over here doing some noise, and let's not forget the Atlantic. So all results of climate change specifically for the region, they present sometimes some 20-25% of uncertainty. So yes, precipitation will increase in 10%, but we are not really sure if it's going to be like that or not. So we cannot really rely on models. I am sure the modeling will improve the results and will provide more accurate results. But so far, it's not like that. Yeah, this is the catchment where I'm studying. Yeah, in this catchment, there are I think there are two landowners. So one owns this piece of land, and the other one, there's another one on top. Yeah. So shrubs are basically in yellow. Dwarf heath shrub is in red. Tussocks grass and the forb that is around, that is super nice for the sheep really look for that. Sorry. Tussocks grass is yellow and shrubs are, wait a minute, let me just check this. Yeah, it's a dark green, and this light green color is the meadow. Meadows are have the highest productivity in grass in all Magallanes. You can have 50,000 hectares, but if you have 50 hectares of meadows, you can sustain a very large population of sheep. But again, infiltration in these ecosystems are very, very scarce. Yeah, and meadows, I just put a picture here, so it's like the valley, yeah, and here it's mostly like peat, but it's not peat, so grass is very growing there. Yeah, and receives all the water from the hill slopes as well. So over there is no problem with water, but all the rest of the ecosystem has. Yeah, and over there I have my four points. So here I'm measuring in the meadow, and over there on top I have three plots that are on a hill slope, shrubs on the bottom, in the middle part is tussocks grass, and on top I have dwarf heath shrubs. So there we're measuring soil water content, specific conductivity and temperature at 5, 25, 50, and 1 meter deep. Since this is the backbone of my project, I say, okay, I'm not going to buy some cheap sensors. I will buy expensive ones. And has been a very good, answer for that. And this measures bulk specific conductivity. And using a method developed by Hilhorst on 2000 to transform or to convert the bulk specific conductivity to pore water conductivity. And the pore water is eventually the one that will move. That's me on the field installing the plots. On each plot we also have special pluviometers, specially designed for wind conditions. Yeah. If you have a 0.5 meters per second wind speed, you are having a 10% error in your precipitation measurement. Yeah. On average, in Magallanes, throughout all the year, you have more than 10 meters per second. So that's 20 times more, maybe, yeah. And of course, when it rains with more wind sometimes, 90, 120 k's. So it's, again, it's important to have proper measurements, yeah. And I also, so with the white pluviometer, I'm measuring bulk precipitation, and with gutters here, I'm measuring what's reaching above, or below the plants. Yeah. Now we will just see the results from soil water content and specific conductivity, because with the precipitation I've been having some issues, because I need to dig and put the pluviometers in a hole, and then it begins, it turns into a pitfall. So insects go, then lizards go, and then rats go. Of course, the holes of the pluviometer get covered, and then it gets flooded. So then it's a pool of things floating there that go birds and so on. So it's, again, there are some issues with the methodology, but we developed a special pluviometer that could solve this, hopefully solve all these issues. Yeah. So what we see here is the plot for the dwarf shrub heat shrub, sorry, that's misspelled, for 5 centimeters, 25, 0.5 meters, and at 0.6 meters here, I found claystone. Also, not claystone, but sandstone, sorry. Super hard, super calcareous, and it's, yeah, well, I started, I had a good time there, and after the 40 centimeters, I said, okay, because nothing was appearing. I really don't know how deep that rock is. I expect to do some resistivity tests to see how deep it is. But here, the blue line is the soil water content, the full soil water content. And the red line is the contribution from precipitation. Yeah. So the first surprise is that, of course, in the soil there was already water, so you wouldn't have these two equal. But then sometimes, most of the time, when soil water content goes up, precipitation contribution goes up. That's, if you add more water, you will have more water. Yeah. That's more or less what is happening here at 5 centimeters. But at 25 centimeters, you are having less water, but the precipitation contribution is more or less the same. Here, for example, it really increases, but then contribution from precipitation is not as I would have expected. That is in dwarf heath shrubs. For tassel grass, you see that the blue line and the red line are almost on top of each other. And you see that the trends, so when precipitation water increases, soil water content increases. So it is why I was expecting. Look at here. Soil water content decreasing and precipitation water increasing again. Yeah. Sorry, summer here is from January until March, more or less. Yeah. And then rain season and snow begins to recharge the soil. Again, here at 1 meter depth. Here there is no change, and it's almost pure precipitation water. The shrubs, more or less the same. And the meadow, again, super spiky, just at the dwarf heath shrub. It's a complex name for that. But anyway, spiking, here it's spiky, a bit split, but then you have this inconsistency. So water content goes down, but precipitation water goes up. Yeah. In the end, well, what I do is I try to read this and interpret it with the knowledge that I have, or that I acquire in the looking for some things like this. Unfortunately, there are not many articles related with this, or I haven't been able to find some like this. But we can sort of conclude that surface soil layers are highly susceptible to precipitation infiltration. So if the top layer doesn't have good infiltration, water simply won't go in. Yeah? It's obvious, it's not rocket science. But for grasses, it's highly important, since grasses have 5 centimeter roots, 10 centimeter roots, and I wouldn't dare to go further. Yeah, and dwarf heath shrubs and meadow show this pattern. High peaks. So there is a high peak on precipitation contribution and a high peak in soil water content. Yeah, suggests a very fast infiltration, maybe a preferential flow. Yeah, especially under dwarf heath shrubs and meadow. Yeah. This is, of course, great for meadows. They are highly productive, they're very important, and they sustain a lot of the sheep production. But dwarf heath shrub is not so good, because it has an advantage, maybe, if we compare it to tassel grass that both lines were super close to each other. Changes in soil water content with or without changes of precipitation contribution could suggest lateral flow. Yeah? We always look at soil from a radar, all big brother eye is looking. But again, soil is something like this. I'm not going to move it, but it's three-dimensional. So water not only goes like this, but also can go like this. So it can go in other directions. And what tassel grass, as in my article as well, shows very low infiltration speed, suggesting low preferential flow. This could suggest that either it's because of dry conditions, and soils there are very, very dry. Or it has few macropores, few insects, few other helpers there to improve infiltrations, compared to dwarf heath shrub that shows a very high infiltration through preferential flows, and it has deeper roots. Yeah, way, way, way deeper roots. So this is what I was going to show you today, but I wanted to add these pictures. This will be super fast, yeah. This is also part of the job I'm doing in Punta Arenas. This is not Punta Arenas, this is Punta Delgada. In that place, the average precipitation per year is 50 millimeters. Over there, wind is super strong every day, all day. Yeah? And over there, we are using a sprayer for I use it for fumigation or to spray products in vegetables and so on. I have a cloud here, yeah. So I put water, yeah, and I grab some volunteers to help me to make it rain on top of grasses over here, yeah. So these are Arduino soil moisture sensors. And here, of course, we can, so after the rain, the interaction of vegetation and water reaches the soil, and then we can see it. We can see the blue, red, and green line spiking or going down. For the last sensor, which should be the driest, I made the calibration the opposite. So it was from the top, and when it received water, went down. And kids were able to notice this. Yeah? They were looking and said, yeah, but either you're lying or there is something wrong. And I say, I don't like it. I don't lie. This is another experience we had. And the whole idea of that experience was to show them what soil is all about. Yeah? So this is a plastic box. Below there is a cardboard like this, with several cleaning, not tissues, but it's, how do you call this? Yeah, pieces of cloth, basically, with different color. And I don't have a cloud for everybody, so that's a PVC tube with some holes. We gave them 1 liter of water and said, okay, first event is 200 mLs. So they had to put the 200 mLs, make it rain, and so on. They could, if they lift the pieces of cloth, they see how deep the water reached in the soil. And of course, the wood would be just bare rock. So we'll only go to the box. With this experience, I showed first what soil does. Then we simulated a high flood, high precipitation event. So the rest of the water just to see how much stays in the cloth and so on. And I asked them then to put this water over here again. It's, again, not rocket science, super, super simple. And they couldn't collect 1 liter of water. So I asked them, well, where is the other rest? It's in the soil. And that is something super simple, anybody can do. And they will understand that soil is the one that needs to have the water. Yeah, because this one is not a waste, but travels somewhere else. It reaches the ocean, and in the ocean has other functions. Please, it's not a waste. I would like to thanks first, the audience, but second, the organizing committee for the invitation, and really has been a very, very nice meeting. I would also like to acknowledge my project that is paying for my salary. This is very important. Yes. Proyecto Impacto, which I'm using really low tech, like those infiltration method, to determine the water retention curve under vegetation, in my case, in the Magellanic Steppe, because I'm interested in the catchment, but this can be also used by farmers, for example. Yeah, it's really, really super, super low tech, and you can really get that kind of information that is key for irrigation practices. If you don't know that, then it's going to be harder. Co-authors in this work that appear in the first slide, Equipo para Explora, which has been super supportive and took me to all these places to make my experiences with the kids. And I am also forgetting, I don't want to forget, sorry, Benjamin Fischer, who is in Uppsala, which is also helping me on trying to understand this hydrological thingies I see, and I need to discuss this. Last but not least, sorry, this is, sorry, thank you. I want to take this last thing, yeah. Maybe it's going to, of course, it will generate laugh. That's the whole idea, to have fun. But also, I think this scene resumes what we are doing. Yeah, we are sharing. There is some knowledge transfer. Yeah, I'm a biologist. Rolf is a physicist. So he took the time to explain me how the physics of that works. I can't remember the name, of course, but you can ask Rolf for that. Look, yeah. In the end, yeah, I didn't want to make it with noise because there were too many other people talking. Yeah? But in the end, you really hear the cap bowing. So it works. Yeah. This transfer, this sharing of ideas, it works. Yeah. I just wanted to say that. That's my contact information. Thank you, Magdalena.
Thank you very much. That was a super interesting presentation, but sadly, we're really cutting into our lunchtime, so we'll have to ask any questions during lunch, I'm afraid. But thank you very much. So our next talk, our next talk is by Jeremi Ramírez. There we go. He's also a student from the University of Costa Rica, and he's a student of the Sustainable Development Engineering course that we were introduced to by Nelson yesterday, and he has a background in agriculture, agro-industry, and he's going to be talking a little bit more about those types of topics.
Okay, thank you so much. Yep. Yeah. Is it with my name? This.
On this.
Yep. Okay, hello everyone. First, I want to say that sorry for my English because I really don't have a very good English. but I try to do my best work. So, continuing with environmental monitorization, I will present my work titled Water Quality of the Moravia River in the Community of Grano, an analysis from environmental and cultural perspectives in a rural area of Costa Rica. I am Jeremi, and as Magdalena said, I am a student of Sustainable Development Engineering at the University of Costa Rica. This research was developed by the following authors: Jaylin Quiroz, Fraser Pereira, Carlos Sanchez as academic advisor, and myself, Jeremi. And also this research was developed in a course of our career. So first, I will show you how this presentation is structured. First, we will start with an introduction, followed by objectives, study area, methodology, results, and finally conclusions. So, to begin, it's important to highlight some general aspects of Costa Rica. Costa Rica is a country located in Central America, historically known for its biodiversity of flora and fauna, and for its abundant natural resources. For these reasons, Costa Rica is recognized as a green country. So, this is largely due to environmental protection policies implemented by our government, and this is reflected in how the land is used in our country. So, according to the figure 1, we can see how the land is used in Costa Rica, and we can identify how around the 63% of our territory is dedicated to agricultural and urban activities, while the remaining 37% is dedicated to 26% for protected areas from SINAC, 4% for forestry or forest lands, and 7% for indigenous territories. The last category is particularly relevant for our research, and we can see why in a few minutes. So, however, on the other hand, like many countries around the world, our country faces water pollution issues that directly impact its sustainability. For that reason, it is common to see a lot of studies that had been conducted to determine the water quality, but only in rural areas, and also to determine how the society impacts in these water bodies. However, we identify that there is a lack of information when we talk about water quality in rural areas, and especially when we talk about the 7% of our territory that is designated to indigenous population or communities that are very close of these lands. So for that reason, our research focuses to identify what is the quality of the water of the Moravia River located in Grano. So for that, we have our general objective. It is to analyze the water quality of the Moravia River in this community, to determine the impact generated by the community on this water body. As specific objectives, we have like a first objective to conduct a physical, chemical, and microbiological evaluation of the water, to determine types and concentrations of the contaminants in this water body. Then we have to assess the results of the water analysis of the Moravia River to determine the quality of the water the water resources in this water body. And last objective, we have to describe the perception of the inhabitants of Grano to determine or to identify the possible sources of pollutions. So, you may be wondering why we choose this study area, and this is the main reason. Grano is a community located on the border of the Chiripo indigenous territories, specifically in the Caribbean slope within the Pacuar River Basin. And in this picture, you can see how Grano is a very rural area. So to give you an idea to where is located this community, we have the figure number 2. This is a map of indigenous territory in Costa Rica, and we need to focus in the point number 9, which is represented in color blue. This point. This is I don't remember the name. I say this is indigenous territory of Cabecar population, and in the market that I'm right now, we can see where is located exactly the community of Grano de Oro. So we identify how this community is surrounded by these lands. And also we identify that this community has a lot of influence by the culture indigenous. So about our methodology, this follows a mixed approach. So we have a quantitative and qualitative part. About the quantitative, 2 sample points were established. The first is Grano de Oro upstream, and this is the point in color blue, and also Grano de Oro downstream, that is located in the center of the community. So the established or both sample points help us to identify how the community impacts in the river, in the Moravia River, because the community is located in the trajectory of this way and is very close to the river. So to determine the quality water, we use 2 indices from our legislation. The first is the Dutch index, and we can see how that this index only considers 3 parameters to determine the quality of the water. There are dissolved oxygen saturation, BOD, and ammonical nitrogen. And also we use different complementary parameters also from our legislation. Our legislation has a lot of parameters, but we only consider 5 because of the capacity of our laboratory. So we use COD, turbidity, total suspended solids, dissolved solids, and fecal coliforms. And about the qualitative part, we applied some semi-structured interviews to people from the community of Grano de Oro, and also to people from indigenous territory, and to people that had a lot of knowledge about the Grano de Oro. Then we applied a file observation with the aim to identify productive activities, practices that negatively impact the environment, and also to understand a little bit of the population's perceptions about this problem. So about the results that we have, as the first point, we have the results from the Dutch index. So according to the table 1, we can see the results of each parameter at those sample points. So it's important to say that this index assigned a score to each parameter, and then we need to add up all the values. So we can see how from Grano de Oro upstream it scored 3, and for Grano de Oro downstreams it scored 5 points. Also we identified that there is a low increase of the BOD, and that would be for the presence of the organic matter in the water. Also we identified a decrease on the DO saturation, and also could be happen or associated with the degradation process of the matter in the water too. So according to these results, we can determine the quality of the water. So about Grano de Oro upstream, it falls into class 2, which is assigned with blue color, and there's meaning that there is not contamination in this point according to the Dutch index. And for Grano de Oro downstream, it falls into class 2, which is assigned with a green color, and there's meaning that there is incipient contamination in this point. So our legislation give us to how we can use the water according of the quality that we identify or the both points. So there are a lot of examples of the uses of the water. For example, supply, in this case, according to the quality that we identify. So in this case, supply water for human use, livestock use water for livestock activities, aquaculture, and also use water for irrigation of plants without restrictions. But what happened? When we analyze the complementary parameters, we identified, although that most of them are very, very low values, and most of them falls into class 1, we identified a very high values of fecal coliforms. The results were 2,400 for Grano de Oro upstream and 2018 for Grano de Oro downstream. So this shows us the importance to use different parameters for determining the quality of the water in river, because if we only use the results of the Dutch index and we say to the community to use the water for these examples, could be represents a risk for their health. So about the cultural aspect, we identify very interesting things, but the main is that are the followed. First, we identified that Grano de Oro is really influenced by the culture of Quebecer indigenous people, and also we identified that this culture has a lot of spiritual connection with nature. So for their rivers, mountains, plants, animals has especially or significant relevance for their. Also, we identify different sustainable agricultural practices. They practice small agricultural in a small scale to avoid the overuse of the soil, so that helps to the environment. And also very important, the ancestral knowledge. They had a lot of knowledge about the environmental education, and this knowledge shared for the generational way a lot on the time. But also we identified that there is very high pressures of the modern development from people that come to the other sites to Grano de Oro and create different businesses. And that's affect in a directly way to the quality of the water and also different environmental aspects in this community. So some issues that we identified is like about the solid waste. People, it's usually to dispose their waste in the river or close to the river. Also, we identify that people is normally to burn or bury their waste also close to the river. We identify a lot of livestock activities near of the river banks. So the wastewater from the livestock activities is coming to discharge into the river. And also we identify that there is an adequate disposal of the Greek water from the houses and also from the different activities of Grano de Oro community. So about the conclusions, about the water quality of the Moravia River, we identified that this deteriorated as it approaches of the community. So this is due to poor environmental practices by the population. Then the high levels of contaminant, such as fecal coliforms, were identified, which may pose a health risk of the community. Then, despite the influence of an indigenous culture that respects and protects the environment, modern development pressures are causing these values to be lost in this region. And finally, it's important to mention that this study was exploratory, so in the future we need to do other studies similar with more samplings and in different seasons to obtain more accurate data on the water quality of the Moravia River. Also, I want to give some acknowledgements, and yeah, this is my presentation. Thank you very much.
Thank you very much. And we do have time for a few questions.
Would the people have any chance to protect their river? Because I'm afraid there are no sewage plants. So what should they do with their grey water?
There is no protection for the people. The people can use the water, and people use the water from their activities. and also it can be represents a risk for their health. But our government doesn't have anything for protect people in these areas.
Any further questions? Yep.
Thanks for the presentation, Jeremy. About the indexes that you used, so you used the Dutch index, and then you measured parameters to see if it's are these indices really used by the Costa Rican authorities for decision making and so on? Yes? Oui.
Yeah, it's a very very bad thing for our environment, because the legislation established these indexes to determine the water quality, and also use the BMWP about the microinvertebrates. But that is all. Well, you can see that this index is not a very better way to determine the water quality of the river, because there are a lot of parameters that we don't consider in these indexes. Yeah, we have a lot of space to improve about that topic.
Thank you. I have more of a comment. And well, congratulations, because you're using like very complex perspectives on a single subject, which is very unusual for an undergrad student. So I want to congratulate you for that. I think it's something very. We often come to this usual conclusion, right? That that land and environment and nature generally is sacred for native people, native communities who live there. But I do wonder why we don't interview more often other people who have other views and who have, for example, policymakers or territorial managers, for example, the municipality levels, and to know what they think about nature, what their conflicts of interest are, and also our own conflicts of interest as researchers, especially because there are more and more researchers doing environmental impact assessment, which are also commodified. These are also sold in the market, right? So I would like to know, I'm not saying that your research is that important. On the contrary, I would like to know also in the future maybe what these other people think about natural resources. We know what they think, but we need to have the evidence. Okay, thank you.
Yeah, I agree with you. We need more studies that, I don't know how to say that in English, but we need to create more studios con mayor complementos de diferentes puntos de vista para mejorar estos temas. Es necesario también involucrar la parte económica con la parte social y claro con la parte técnica. Es importante poder unir todo. Gracias.
Very, very short question.
From a solution seeking point of view, it would be really interesting now to see how high how important the sources of pollution are between grey water and cow dung. Do you already have a feeling of how much is attributed to agriculture and how much is attributed to the private use?
Yeah, I think that all of the activities are private in a private way, but we don't identify how many % of this water is from the agricultural activity or where it is from other kind of activities. But in this community, really had a lot of livestock activities. And also they use usually the water of the river for their practices. And also they return the water from the river. Yeah.
Thank you very much. And well, first an applause, please. And we're again facing a decision, and I think we're going to do it democratically again. How hungry is the crowd? Who wants to have lunch now or later? So as per our plan, we still have one more presentation by Carlos. But so I think we can have one more presentation before we... Good. Okay, then we'll have one more presentation by Carlos Martinez. So we already presented him previously, but it's always a nice thing to present people again. Carlos Martinez is one of our, well, by now I would say long-standing partners from originally the UNICAES, but also at the Universidad of Sonsonate, where he recently got a new post. And he is has a lot of expertise in information technology and system management, especially AI-based phenological analysis and growth yield correlation in maize using, for example, GNDVI and weather data. And he's going to explain a little bit more about that to us.
Well, thank you very much. Fortunately, I was just told that nobody of you is hungry already. We have that in advantage. Basically, we're going to make this very brief. We analyzed maize crops into artificial intelligence to test the models, how well they could go with a forecast of plant development. And this is the current situation in El Salvador. It is very alarming. There are some stuff that should not be happening. The poor soil management, you can see the runoffs degrading the soil quality and fertility, and also dragging plant pests like nematodes, uneven coloration. Well, I don't know if the projector make it very clear, but this is kind of more yellow than this other area. That's because soil space variability well not managed. Our topography is very complex. We have like 3 different slopes here at least that makes easier for the farmers not to do anything. Shouldn't be like that. And plant stunting. This is the result of so many bad combinations of management practices, and that leads us to a problem. How is going to be the food produced? How am I going to feed my country? How are farmers going to keep productive if they are incurring in so many bad practices? And well, before addressing the correct way to approach to the problem, I made a systematic literature review. I used Scopus and Google Scholar for some old foundational articles. I followed this path, but at the end I stayed with 108 articles about the use of artificial intelligence to understand these problems in maize. And this is, well, please not read this at this moment, but this is very interesting. They have been using artificial intelligence in farming, analyzing environmental impact as well, maize parts identification, maize development, remote sensing, and you can see that China is appearing in everywhere. And probably as we speak now and die of hunger, no, just kidding, many more Chinese articles are being released at this time. So it is very hard to keep up with them because they produce the drones, they produce the technology, they produce the software, they test it, They publish the articles and then they sell it. By the time we get the commercial product, it is already published. So what can we do to analyze our situations and produce knowledge but applied to solve our current problems? And this is what they have been doing. They have been using these technologies for analyzing support vector machine algorithm of artificial intelligence. For example, random forest is a common pattern. It is a really good and fast model for machine learning. And the vegetation indexes that measure how well crops are performing, they are all going around NDVI, green NDVI, which are normalized color indexes. And well, some of them have used drone imageries, actual photographs, and satellite images mostly. So, what's the gap? Everything seems to be covered already. Everything seems to be studied. What can I do? Which is my contribution? What can I do? Well, the objectives were to develop a low-cost methodology for monitoring maize in the subsistence farming conditions. What could be a low-cost and easy way to analyze multispectral information while plants are developing in a very limited environment? Then validate the method for calculating the GNDVI and leaf area index, which is called LI, which is a measure of how well the plant canopy is developing in terms of area. And also identify the most cost-effective artificial intelligence approach by using random forest as a baseline. As I told you, random forest is a very well-claimed model for analyzing almost everything, but there are more models, and I wanted to know more. I wanted to compare. So, knowing that random forest is so very well claimed and documented as top performing and accurate model, I used it to compare the other models. So, I came up with this. I took several fields, 5 fields of maize in subsistence production, and there were several flights in different plant stages to track how the green colorations and the lie or foliar area was developing in every stage. I took eight stages. And I used random forest. I used binary thresholding. This is not machine learning. This is a image processing library used in Python to analyze the imagery, but not using machine learning. This is previous to machine learning, but it is not bad at all. And I made a hybrid. Deep neural networks and convolutional neural networks with mobile net are the top of the most fancy stuff around, but they have to be fed with some previous information. They have to be trained. And training information by annotating images of crops in a subsistence farming agriculture is more than a pain. It is very hard. You don't have the resources, you don't have the time, you don't have as many people skilled enough to do everything. So I used a hybrid model, which is K-means used or developed to detect images and segment them to create annotations. So the machine learning did the annotation part, and then I used those models to feed more advanced neural networks. And well, before, I forgot to mention, I also took into consideration the climate. It is not very well integrated yet in the prediction model, but we still have some stuff to do. And these are the parameters about climate. Let me see. This is the accumulated precipitation. This is noise. This shouldn't be here. And this is temperature. This day is impossible, 300 centigrades. that's too much. I mean, sensors were not producing anything good. And we used, thanks Rolf for giving some advice with this, isolation forest to cut these anomalies and to make kind of better the tendency and the prediction, to fill in the gaps and taking out the bad numbers. This is about the temperature. This is not very accurate, but because this is one season only, more seasons are coming. And this is the GNDVI for orthocomposed multispectral imagery. This is not the actual picture, let me tell you. This is not a RGB picture taken by a drone. This is a multiple series of multispectral images coming from infrared, far infrared, nor near infrared, green color, and red edge, composed in one single image, and the software makes a normalization of the colors. Everything that falls into the range of this, of the majority of the plants are given a threshold of colors. So that's how maize plants are distinguishable of some areas which are not maized. For example, these areas over here, the lightest green colors are grass, and the darkest are maize plants. And this is how the question arises. How is this going to be calculating effectively my crop health? Well, using artificial intelligence to discriminate the colors. Okay, first, binary thresholding did quite acceptable. This is not artificial intelligence, but created these masks. These are the masks that indicate which pixels of the image, the normalized image of the raster layer of information, are actually maize and which are not. This is why this looks like very old stuff. This is black and white because, yeah, one means yes, it is maize plant, and the other one means no. Yeah, basically in this case, white means yes, it is a maize dense area, and the black is not maize. Could be grass, could be soil, could be, or probably maize dead leaves. Could be maize, but dead. And this is what binary thresholding could do, and this is what K-means unsupervised masking technique could do. Well, kind of seems that binary thresholding performed a little bit better, but it was intended to refine the performance of K-means by using these masks to train convolutional models or dense models. And these are some results. Random forest, here you have the binary mask, and this is the substitute colors, the actual colors from the imagery, but through a substitution inside of the mask. Okay, up here, this is the result from random forest, and this is the result of dense model. It is kind of similar to the eye, but to the computer, this is not similar at all. Random forest allowed more yellow pixels to pass through the mask, and the dense neural network is limiting the pass of green, light green, and yellow pixels. And, well, here you have some predictions, some messy linear graphics. And the binary threshold looks quite good in stages. This is the accumulation of leaf canopy, leaf area index of the plants. And the binary thresholding says that this goes from 1 to 6, kind of good. At the end, we reach to a point that has to decline. This is normal in maize because plants start senescing or start dying. That is the natural process. So a decrease of leaf area was expected, and random forest was a little bit flat, but remained accurate. K-means was a little bit crazy. It was not developed for detecting these kind of images. It was developed for other applications like image segmentation of more distinguishable colors. This is too similar. The green from plants, which could be grass or no, or could be crops or no, are too similar, so it didn't perform very well, but I said, let's do it. Let's still do it as a training annotation. And these are the performance of the dense neural network and the CNN, and they are kind of alike. Not as good as random forest. It is very hard to be beaten, unfortunately. And random forest is very, very fast. Not much computing power is required. Even my laptop from the office was capable to run a random forest model, but the CNN and the DNN are more complex, have more layers of activation for processing imagery, but they need more computing power. So there are more advanced models, yes, but more time and resource consuming. So why don't we keep it easy with random forest? Could be. This is the GNDVI prediction, the prediction of how good the chlorophyll reflectance is doing in plants through different stages. Stage 1 is the baby plants, and stage 8 is the senescence period of time of the plant, which means that it is starting to die. Binary threshold and random forest perform very equal. It is kind of very flat. That's because farmers applied nitrogen since the plants are very tiny, and that's how they keep having the same color. They are applying ammonium sulfate. Our soil is very low in sulfate, so when people add ammonium sulfate, the green intense color manifests in maize plants. We are not adding magnesium, for example, because our soils are very rich in magnesium and also potassium. And this is why it seems like the color is like a standard between 0.3 and 0.35. This is a index. This is not a percentage of saturation of green. The green DVI is an index, so this is quite possible. And we can see here that K-means resemble a lot the results of the dense neural network, which is not that bad. We have a lot of noise at the beginning because of the presence of tiny maize plants compared with big and huge wheat plants. And then CNN, it was crazy. Could be better? Yes, it can be better, but it means that we have to annotate more images to perform more activation and fine-tune better the models, which takes more time and more power to do what could be with binary threshold and random forest. It could be achievable with both. So these are some metrics. Random forest offered very high accuracy and precision. Binary threshold had a low accuracy but high precision, and the other ones were, less effective. Can this be improved? Yes, it can, but this is not cost effective. So in conclusion, the known AI prediction based on color thresholding is possible, but not that accurate. Random forest, it proved very good accuracy, as in the systematic literature review, that means SLR, as most of you already know. And the supervised deep learning models can learn from annotations coming from a machine learning model called K means, yes, it is possible. A hybrid model functioned, not that well, but did. And their performance was reduced compared with random forest. Next steps, well, integrate the weather and yield data to the hybrid model of detecting or predicting the plant developing. It is just one part. Weather data and crop outcome is not still integrated in the model. We're in the process. It is required to fine-tune the deep learning models to configure it best in order to obtain better performance of machine learning and deep learning structures, which means adding more layers and more samplings and more everything to the code. It is still subject of analyze how far we can get with this, because it has a limit on model proficiency according to the information we are providing. We still have to see more. And we have to compare the accuracy of multispectral images versus RGB images. That's the next step. What I could see in this systematic literature review is that not even in China, all of the researchers are using multispectral. Some of them are using just based RGB because the drones are cheaper. But what I could not find is a balance or comparison between the accuracy of the models with one technology and the other. I could see just plain RGB through many lands. I could see a lot of artificial intelligence going in through multispectral, but not the comparison. So my question is, could I produce achievable results which could be promising using just RGB, yes or no? How good, how worse, I don't know. And I couldn't find it in literature. So those are the next steps. So thank you very much.
Thank you very much. We do have time for one or two questions. Or lunch. Maybe everyone's just anticipating lunch a bit too much. So we'll head straight into it, but before we do, I wanted to kind of point out we have a little bit of a wall, and this is because we're anticipating a change for exchange dialogue. Sorry, before I do all of that, please, a round of applause. So we've been talking a lot about cooperation, how important it is to form these friendships. So Camila had this idea, and Johannes Pfeiffer, who will later be moderating our workshop, and we've just kind of shared those ideas. If you have something that you guys collaborate with, you know you share similarities, you know you have some ideas in common, just take a post-it note, write it down. It can be one word, it can be a whole text, whatever, but we can give you the lunch break to kind of talk with each other and find commonalities, similarities, and, well, good eating. Okay. Yeah. Okay, everyone. I think we can start to settle back down. The edge people can also come back. All right. Okay. I think we can semi-start. One small note, so you saw a lot of kids go in, I forgot to mention, those are from the Young Creatives group, and they're doing their workshop right now, but in about half an hour, hopefully, we will have the workshop with Antonio, and he will be doing it with children, but I want people to be able to watch, because it's really cool. All right, but for now, we also have something else really cool. Lisa Schilling is going to present an polar orbiting weather satellite. She's a graduate from Hochschule Rhein-Waal. We've heard from her on the first day. And she's earned her bachelor's degree in media and computer science. She is now continuing her master's studies. Yes, very good. And hopefully will gain international work experience afterwards. And so I welcome Lisa Schilling.
Okay, hello again. This is my second presentation on this conference, and I'm very happy to present you another antenna I built. So the title of this presentation is Tracking Polar Orbiting NOAA Weather Satellites and Receiving HRPT Signals. Very fancy and long name. What it means essentially is I built an antenna to receive satellite images directly from space. So this was part of my bachelor thesis, and I built this antenna. It consists of a parabolic reflector antenna and a tracking device. And yeah, the tracking device is this part right here. It consists of two axes. So this is the elevation axis. It can control the elevation of the antenna, and this is the azimuth. And down here, you have the electronics compartment where everything like the microcontroller is, and this controls the movement of the motors. So the satellites I'm tracking are polar orbiting weather satellites. You can see right here their orbits. So polar orbiting means they go from north to south as compared to maybe west to east. So this is their orbit, and there's basically 3 satellites that I am tracking. So NOAA 19, NOAA 15, and NOAA 18. They're all weather satellites from the American weather organization called NOAA. And theoretically, you could receive a lot more different weather satellites with the very same antenna that I'm about to show you. I just focus on these for, keeping a bit simple. But Europe has a few weather satellites you could receive, Russia, China as well. So you could get a bunch of different images. But yeah, these are the ones that I'm tracking. And as these satellites orbit Earth, they take pictures of the Earth. You can kind of imagine it like your scanner at home, like your printer. When it scans a document, it just like takes a line and goes to the next, takes another line. And that's kind of how these cameras, you could say, work. So they take these cross-track scans of the Earth, and in real time, as they take these pictures, they also transmit them towards the Earth's surface. And this is exactly what I'm receiving. So this is called the high resolution picture transmission, short HRPT. This is what was in the title, the HRPT signals. And to receive HRPT, essentially you need two things. You need a tracking antenna. So a lot of receptions you could receive with a stationary antenna, but in this case, because the frequency of HRPT is a bit higher, you need an antenna that actually tracks the satellite. So it can't just stand still, like, you know, upright. It actually needs to follow the orbit of the satellite as it flies overhead in real time. And you also need quite high gain for the same reason, like the frequency. So, what I did for the tracking part is I built the tracker, as I already said. And for the high gain, I chose a parabolic reflector antenna as my antenna of choice. So a parabolic reflector antenna, like this one that I built for my thesis, is nothing else than like a satellite dish. I think everybody knows those. Usually you use them to receive like TV broadcasts or something else. And they work by basically every signal that comes in here gets reflected into this feed. For the commercial ones, it's usually offset, so it's down here. But in my case, it's a prime focus dish, so it's in the center, you know, the focal point of this parabolic dish is right here. One of the main objectives of this whole thesis was to keep things cost effective. Because receiving HRPT in itself is nothing new. The transmission has existed for quite a bit, and professionals can receive it very easily. But receiving it like at a university for students or for pupils is something else. So my main goal was to keep this cheap. And as you can see, I did build my own reflector. But why would I do that? Maybe someone is wondering why I didn't just use one of the commercial sat dishes, because by no means they are not expensive at all. They're very cheap. But the problem is that they're quite heavy. So these can weigh like from, 2 to 8 kilograms. And that's kind of not good when you want to build a tracker with cheap motors. You need like a lot of torque to hold this kind of weight and keep it stable as well, you know, and move it. You know, you have to hold the whole thing at this angle maybe. So I had to find a different solution. And that's when I came across this design on the right. This is from a Japanese engineer called Yoshiyuki Takayasu. And I think it's a genius idea. So he has used kind of these, maybe some of you have seen geodesic domes before. It's kind of this idea. And he uses tangent struts to build a parabolic shape. I didn't really have the calculations to do this exact shape. Like, you know, you need very specific lengths. These struts, they aren't pre-bent or anything. When you cut them, well, I used wood, he used aluminum, but it's the same. It's like 2D, you know? It's just a straight strut. And if you have the perfect length, when you connect them, at these points, it automatically bends into a parabolic shape. And that's what's happening also right here. So with the help of my professor, we helped me like set up the equation systems to calculate this whole thing. And then as soon as that was done, I was able to cut this with the laser cutter. And the construction itself is very easy. So as you can see in the end, you just have like a small sketch in Fusion 360 in this case. I cut it with a laser cutter, you connect everything, and then you put like aluminum mesh on top of it or behind, doesn't really matter. And the nice thing about these meshes is, as long as the meshes are smaller than half of the wavelength you're trying to receive, it acts like a solid surface in the eyes of the frequency or the signal. Then we have the feed. As already mentioned, this is the actual antenna. This is just the reflecting part. And this is the part that actually receives the transmission. So this is built for HRPT, for the frequency, which is around 1.7 gigahertz. And I built this with the help of another company here in Camp Lindford. They're called our front end. And they helped me with the simulation. So this is what you can see on the left. This is the simulated part of the 3D model that I designed. And then on the right, you have the actual feed, which is also very, very easy to build and very cheap. You just have one copper wire that you twist. And The rest is 3D printed and then a ground plane. And that's basically all you have to do, and done is your complete antenna. Then we have to go and build our tracking device. This is a bit more complicated. We have, as already mentioned, we have the elevation axis, which is this one, and the azimuth axis, and then here you have the electronics. Most of it is just 3D designed and then 3D printed. So I used Fusion 360 to design everything, and then I just printed it out, connected it with screws and bolts. I also used the worm gears, which were pretty nice because they add a lot of torque. Okay. Inside of this electronic compartment, as I already mentioned, is the microcontroller. I'm using a ESP32. Pretty nice because this already gives you like Wi-Fi connection. So how the software works, you know, that's on this chip is sends out an HTTPS request to a website, and this website gives you data called two-line element sets, short TLE. And these TLEs are like snapshots of the satellite's position at a current time. And to use these data, you kind of need to calculate the entire orbit of the satellite from them. So there's an algorithm for that and libraries. You don't really need to worry about it. Pretty nice. Just integrate the library into your code and then you're done. So that's how it works. And then after everything is programmed, you know, just imagine the tracker is done, your antenna is done, you need to set up the transmission line from your whole antenna, from the feed to your laptop. So the same as with the Ofenrohr I presented earlier this week, you have a coax cable, and on there is a low noise amplifier, this part. What this does is it reduces the noise in your signal and amplifies what you actually want to receive. And then at the end, you have the software-defined radio, the SDR. It's just like a radio, which is very, very adaptable to a lot of different frequencies. And yeah, it has a USB dongle, goes right into your PC or laptop. And on there, you have this very nice software called SatDump. It takes a lot of the work off your shoulders. So what you can do here is you set your target frequency, which is about 1.7 gigahertz, and then you can see the signal being received here. So I was at the terrace at the Hochschule over there at the building, and this is the center frequency of the HRPT signal. This doesn't actually have the data lies in these sidebands. And like the higher the difference is between the base and, you know, this little part is showing you how well you receive your image. This isn't actually that bad, it's just the scale that's a bit off. Yeah, and when you're using this, you can see, okay, the signal is there. Am I capturing the satellite correct? You can then record the signal you're getting, and in the end, the software also helps you demodulate and decode everything. And when you have done that, you receive a directory with a lot of different images. Some of them are these images. I know they're not perfect, but I'm very proud to have received them. So the noise you are seeing comes from a problem with the azimuth axis. So there's a bit of wiggle in there. So, you know, if wind maybe hits your reflector, you can get a bit off, and that's when you get the noise. But otherwise, these are the images. As you can see, they're all over like Europe. You can see Great Britain, Ireland, Germany, France, and so on. And of course, this is because I'm here, so the images will also always be at of the point you're at. Okay, that was it. Thank you so much.
Thank you very much. A very interesting talk as well. And are there any questions? Yes.
Hello, thanks for the presentation. Just wondering how much is to build a setup like yours, for example?
How much money you mean, right? So the whole setup with everything included, also the electronics, was I think, yeah, 430 euros for the entire thing. Yeah.
Any other questions? Yep.
Thank you very much for your very, very nice talk. And the pictures were already quite impressive, but what can I do with that besides looking at the nice pictures?
Well, I didn't do anything with it except for looking at it and being very proud of it. So in general, HRBT is used for environmental monitoring, you know. So weather stations use it to predict the weather, and you can also use it to kind of see the development of the climate change, kind of, you know. Maybe more to the north or south poles, you can see how, well, the ice develops, or they also use it to track maybe oil spills on water, or when there's a hurricane coming up, you can also track those, or any sandstorms. I've seen a lot of different images. But yeah, in my specific case, I don't have an application at this scale.
Thank you very much. I also have a question. At what scale can you, is the resolution basically? Like how far could you zoom in, basically?
So if I'm not mistaken, the resolution of these images is per pixel is 1 kilometer. So this might seem bad, I guess, but there are other transmissions like APT, for example, which is the automatic picture transmission, and there it's 4 kilometers per pixel you can see on the image. And these images are very large, like the files are huge when you receive them, so you can zoom in quite a bit.
Well, thank you very much. And yeah, I think there was no other questions, right? Yeah. Okay, thank you very much. Okay. Now I have to go back another page. I mean, I don't quite need this to introduce Harley Lara. You've also all seen him all week today. He's been our tech genius in the background. He is a HSRW student, and now he's also at the Hochschule, Bonn-Rhein-Sieg it is, and he is actually from Nicaragua. He's a mechatronics engineering student specializing in control systems. And yeah, he's been a very, very important part to all of these processes, and he's going to explain a bit why.
check, 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 check. Yes. Okay.
Hello?
Check, check. Okay. Yeah. Sudah,
Check,
sudah.
check, check.
Oh.
But it's not coming from that microphone, right?
Yeah. No.
I think it's like a general...
Yeah. Interference, yeah. Not sure why. Check, check, check. It's this thing.
It's this one.
Yeah, this thing. Okay. Okay, it's this channel. Check, 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 check. No.
It's really bad.
Yeah. Okay.
You can just do it without. Yeah. Just be recorded.
Check, 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 check. Okay.
I think it's fine.
Okay. We are back. Good. Good. Yes, we have a bit of noise, but okay. Welcome to the last presentation. Hope it's not too doesn't take too long. So this presentation is about applications for drones in basically low light conditions. Right, we will showcase some applications and some limitations, and but to actually motivate the discussion, why this presentation, we would like to show you representation, how the idea became to life, basically how it burned. Yep. So there is this situation. We were in the lab one day, and suddenly Jan was like, "Okay, yep, I need to install some sensors."
Yeah, I just need to install some sensors in the mine, Harley. Would be cool if I can also fly the drone in the shafts, you know, to get some images. But, you know, it's very dark and I don't know if it would work or the drone might fail. What do you think?
So we were like, okay, let's think about it quickly. And then we come up with the idea, a brilliant idea. Let's add some LEDs, right, to the drones and see what happens. Right, so that basically, let's try, and that give us to the next slide, which is sort of a disclaimer, right? This is not a formal research, it's not a project, it's a side activity, right? We have actual project that we have to manage and handle. So we were like, let's explore this. We have drones, we have resources, let's try it out, right? So done spec, nice tables, analysis. We will show you images and some results and insights. Yep. So the actual first question is, which drone should we use? Because we have a lot of them. And you can see here the range, we go from 20 centimeters to 3.2 meters. So we can go from 20 grams to 100 kilograms. Of course, you need to pick the right drone for your application. So that was the first discussion. So we have two options in the lab, because we have a catalog of around 25 different drones. We were, okay, let's see, what do we actually need? We need a drone with decent cameras, right? To be able to visualize the environment, but small enough, and they're also able to carry weights. So we decided to go with those two as a testing platform, and then we like formalize the requirements by saying, yep. We formalize the requirement, let's say, okay, let's build a drone, let's go with the DJI Avatar, because it's the one that doesn't have LEDs, so it's completely blind in that sense. Let's just equip this one, right? But there are some limitations, of course, and for the DJI Avatar, the main limitation, for example, is the payload, so you can carry it up to 90 grams, right? So you have to be careful with your LEDs and possibly battery. But you will say, but you know, drones need batteries, and there might be a battery already in. But this is a commercial drone from DJI, and they don't like you to mess with their hardware, so you are not allowed to basically attach other payloads into your drone. So if you want to power up your LEDs with the battery built in, the drone will not even start. Yeah, there are some safety mechanisms internally, so we have this limitation. So we have to add our LEDs and our own battery and our own, let's say, power supply system for the LEDs. So then we start doing some design, doing some electronics, some research, which one would be the best electronic design for this. We have some limitations also regarding budget and time, right? Because we didn't have much time. This is a side activity. So we research a bit. Let's pick some electronics. Let's put things together that doesn't require much effort from our side. And we come up with this, what we call an open design. It's just a power supply that can supply enough power for powering 6 LEDs of our specific needs. And you can also visit the project online. It's also public. And this can be not just for LEDs. This design, it's also for sensors in general. It's a 5-volt power supply. So you can use it for any other application within our scope. So of course, after design, you have to do some validation just to make sure that your prototype and PCB works. So we did some small experiments and tests to validate the design, basically. And you can see we went from the 3D design and the PCB design, electronic design, to the actual real world test. And you will see that this 3D thing that exists just in your computer as a digital format became basically a real object on the right. And now we have to profile this, how it performed. Is it performing as expected? So we were running some tests to basically check the limitations and performance of the platform. So we were just checking here, for example, power capabilities. If it was able to basically deliver enough current and voltage for our LEDs, because we need quite some. We need actually 25 watts to power up 6 LEDs, which are roughly 5 watts per LED. Yep. And of course, with this limitation, you need to account for thermal dissipation, which also a critical situation here because we want to narrow down the space and the weight, so we have to make things smaller. And when you make things smaller and they use a lot of energy, you need to dissipate a lot of power, right? This is a high efficiency actually design. The efficiency in max consumption, it's of 96% of efficiency. And this 100 degrees is actually expected from specs. So we are expecting this to get that hot. So we were just validating the design. Yep, so on the next, Jan will talk to you about the testing sites.
So we were running in 2 testing sites basically, and it was very hard to find them because they need to be unbelievably dark. Like we don't want any light in theory. So we were running with 2 sites. One had still a little bit of light. The other one was the mine. First one is the St. Victor Dome, the cathedral in Xanten basically, because that is also a part where we see this technology, let's call it, has application. And the other one is in the Neuhoffnungsstollen that I already presented in my previous presentation. And why would this, for example, be needed in a church? And this image is a very good example of that basically. They are smaller churches, but this one is quite big. And you can see to reach basically the ceiling over here, they need to build huge structures, which is very time and cost inefficient, maybe I would say, just to reach basically the top, basically just to reach the top ceiling to do some maybe restorations, but also for inspection, it would be the same case. So if there are any cracks or anything, you have to do this basically to do an inspection. Flying up there with a drone though, that maybe has some good light, so if a good view on the structure would be very beneficial in this case. We flew more precisely here in this left northern tower, as far as I remember. Here you can see us. We were basically first planning out the mission. What do we want to do? What do we want to inspect in that case? We had our LED, we were preparing our drone basically, plugging in the batteries, mounting all the LEDs onto it, getting ready, powering the whole system on to do basically our first test. And it was flying in there. Here you can see this is the tower, and the hard thing about this, I showed you before, there was this huge structure to the ceiling. Here you could not even get the structure into the room. So to basically get up there, you would need ropes basically to climb up there. With a drone, this is way easier. We were using basically an FPV. You can see me here. You can see me over there with the goggles basically, and Henrik basically holding the tablet so others can also see what I can see basically. So in like a real world scenario, there would be someone flying the drone manually, and then there's someone basically who has the knowledge of inspecting and can analyze the images, but of course we also had recordings of that. Yeah, that was basically what we were doing there, and it was going okay, but we saw some limitations basically in the accuracy and the stability of the drone, but with manual flight it was manageable. Then we also flew in the mine, in the Neuhoffnungsstollen, and here we have some videos that we want to show you. Just press again. Yeah. Here you can see, so this video is taken by Thorsten. Thorsten is from the other university, who is also very interested in this. And here you can see, this is an area that you normally could not get to. It is just not possible or way too dangerous to basically get there. So the drone is right now flying in a weather shaft, it's called, that gets fresh air into the mine. And this one, yeah, you just can't get there basically. You could not fly up there. And then there's a 12-meter hole basically where we could, with this one, inspect the walls. Yeah, but this is, as you can see, a very broad space that is maybe easy, one would say. But then we also have this one. The benefit of this drone would also be to go to very narrow spaces basically. So this is in another part of the mine. It's the old machine room. And normally you wouldn't go there basically. There might be stuff falling from the ceiling. So going there with a drone is in that case beneficiary because you don't get yourself in danger. And with the LEDs, you can see one limitation. They are too wide, or they need to be a bit more streamlined. They're a bit more narrow. But this one Harley flew, and he can get through very tight spaces, which should be come up right now, right? Because there it comes. Would be good to even have it brighter. Yeah. So now you can actually see it. And you can see now there's some debris basically coming up, but the drone is small enough to basically go through it. Yo, should I already continue to the next one? Yo. See? We did a second test with the other drone that we previously introduced, and this one we didn't equip with LEDs. We used our helm lights that we were basically shining in the direction where where the drone was flying. The advantage of this drone was basically that it already had one LED pointing downwards, which it needs to get its location better to stabilize. But this is also an area we asked Thorsten, hey, can we go there? Because there are stairs on the side. He was like, yeah, I would not recommend going there. This thing is very, very unstable. And here again, so basically for like a lot of years, no one ever was up there, but with the drone, we were able to basically fly up there and do some inspections. Is there still something there worth of interest? This one, Harley? Yeah. Oh, this one as well.
Yeah, I better sing the streaming. Okay, for this image, I just want to give you a bit of perspective of the actual difficult scenario. Because the previous scenario, they are difficult, yes, low light, but you see the spacing is quite broad, so you have a lot of space to maneuver the drone. So, but that's still interesting, but the actual interesting part of the mine is a part which is very narrow, and it's actually very dangerous to go as a person through it. So I want to give you some perspective. We need to go through this hole, right, which is this big, right? So just as a give you some perspective scale. So we actually, or I went, also Jan went through this hole just to visually see the place, because also Thorsten, the professional, told us that we can go there safely with him, just to check the actual environment. So then we can fly the drone from the inside, because it was almost impossible trying to get the drone autonomously, or let's say manually, through this hole, because they have some obstacle avoidance, and the drone will basically refuse to go in such a narrow space and say, nope, you know, that's too dangerous, I will not go there. Like, if you want as a human, you can go. Yeah, we went there. And this is the picture inside, right? So this is the actual interesting place in which the drone with light will shine. I mean, it will shine, you know. So this part, you see those beams, metallic beams, they used to hold the structure, but now they are completely unstable. So there is no way to get someone through that shaft to basically do some inspection in the back, because the actual interesting part is not this one, the one that we are looking is the one behind it. What is behind this? So they want to explore if there is any other room or place that makes sense to enable or completely close this area. They need to inspect the mine, because there might be something happening in the back that can damage the overall structure of the shaft around. Yeah? So it's really, really important for them to have a visual inspection of what's going on behind this. So behind this is actually, this is 0.7 meter wide, right? Really, really narrow. We tried to fly the drone in there, but the drone was refusing to move, right? Because it's so narrow, you have some obstacle avoidance sensors, so it didn't want to move. But we need to go through that 0.3 meters gap, so 30 centimeters. That's quite small. So yeah, so you see, this is the actual part that make things really, really, really hard for the drone. And of course, there are some environmental challenges that make it even harder for us, which, for example, is extremely dark, there's no light, there's also no GPS, so you cannot rely on external source of positioning. There is also high humidity, so you need to account for this for your electronics, right? You need to account for really, really humid environment. There's, in some places, sudden gust, so you have those airflows going through, for example, this shaft, which is for ventilation. You might have some airflows going on suddenly and can affect, for example, the positioning of the drone. You have flying particles, right? Of course, you have a flying object, which is producing an airflow that then leave a lot of particle and dust. So basically, the drone in very narrow spaces with a lot of dust, you have a cloud of dust, and you need to be able to maneuver and hold position in this really, really hard environment. You have water drops, you have also wet walls and wet floors. You might say, let's put some LiDARs and let's rely on LiDAR instead of visual inspection. But in this environment in which you have a lot of humidity and water, you have a lot of reflections, so your rangefinders and your sensors which measure light beams will fail, right? And of course, you have weak or basically not communication in some places. So it's really hard to go through rock, right? So we have also some limitations from the platform perspective, from the drones that we are using. For example, the DJI Avatar, which is the FPV drone, it was very unstable under load or not light condition, even with the LEDs. So it doesn't seem to be reliable. With the DJI Mini 4, for example, this one with the down-facing LED built in was able to hold the position quite well under low light condition with a single LED, but it refuses to go higher than 2 meters, right? So to get actually to this video of the stairs, which is more than 2 meters high, we have to trick the drone to make it believe the rangefinder is not actually 2 meters. So I step below the drone, put my hands on the sensors, and then we can trick the rangefinder sensors so I can go a bit higher than 2 meters. And both drones, for example, present this quite nice feature for outdoor that you can avoid obstacle, but this is actually bad for these very narrow spaces. Of course, we can disable those, but they make the drone very unstable because there is not a positioning system and it's not aware of the environment. So then the drone can collide with the shaft, and then the shaft can collapse. Right? And of course, we learned that you need to use a bit more narrow LEDs, so try to point the light more directionally so you have better view, because as you can see in the video, it's quite dark even when you have a lot of space in front. Yep. Of course, just remember this is not a formal research, but we did some research on commercial solutions. Can we get a drone that was able to do this? Probably not. The prices are quite high. You can see here more or less price range. What do you want to get a commercial drone? And the average price of those are 46,000 euros, right? If you want to get a commercial industrial drone that is able to do this. And those guys, as you can see, they are quite big. You can see here the width 40, 40, 60, 40, 42, right? The one that we are using is 20. Flight times also quite limited. The average flight time is 13. Our drone can fly 30 minutes, actually, with the payload on top. And you will see there is a drone which is very, very cheap. It's just 6.5. It's actually what we are doing, but without paying this price, because we have the drone, we have the LED, and we equip our drone with basically virtually no budget. It's essentially the same solution. So you will expect this solution, this commercial solution, to behave as our solution, or closely. Yep.
And this is a bit related to it, but for example, we last year, Angelina Besser was doing a bachelor thesis with us. This was more towards museums, but she really did many experiments, and she even saw in the mine LiDAR or laser-based technologies for basically for holding the position or something wouldn't work. She wanted to make 3D models, and this is one part that might also be an application, not only inspection, but also get 3D models of the photos with the videos to use them to show other people basically the history behind the place, to make the places that are normally not accessible to people accessible again through other technologies. It's just a small side thing, because going to such places is just dangerous sometimes, and with this technology it might be possible again. Thank you very much, and thanks to Ali to creating most of the presentation. I was more the guy, hey, we should fly a drone there. Any questions? Welcome.
Okay.
Das geht nicht mehr.
Ah,
Das
okay.
ist in the stream. Im Stream noch da.
Okay. Are there any questions?
Are you thinking in the near medium term to add some sort of positioning system that the drone by itself will detect the floor, ceilings, and whatsoever? So you don't have to pilot?
Yeah, there are different challenges. For example, one of them is communication. We were doing all manual flights, so there are certain parts of the mine which are very hard to reach through manual communication. So you would rely, for example, in autonomous flying drones, so they can reach really hard places without the need of one-to-one communication. Another thing regarding sensors, of course, we can add sensors for the drone to improve the positioning system as cameras, but for a camera you will need light. Or we can rely also on cameras that don't require light, like the events cameras, for example, that were presented before. They don't require much light because they are based on events, and you can equip them with some extra light. But those are quite expensive, and they're still quite bulky. For example, event camera, the smallest one, can around 300 grams, right? Plus power, because you need to power up the camera. Of course, we can go with LiDARs, but LiDAR, same situation. You have very humid environments, and you will have a lot of reflection on the laser beam, and you will not be able to reach places. I think, in the end, a combination of multiple sensors can help to go through the places. Yep.
Yeah, just for, it's okay, yeah. Yeah, just for comment that, yeah, right now there are some applications around using even cameras with drones. ETH Zurich is leading with this kind of sensoring platforms, but hardly say the same problem is that when the drone is in movement and also the camera is going to be in movement, they are going to generate several events. This of course implies that you need a very good, powerful GPU. So yeah, from one side, of course, it's going to be nice if it is in a static scenario, but in this case, it's going to be maybe not so good. Yeah.
Seeing like these environments in the mines, I somehow started to think about balloons. Because I think they are way better into bumping things without destroying them and destroying themselves. Or some mixture of drone and balloon might be interesting for that task.
Definitely, in the end, if you want to do a full inspection, you will need to rely on multiple platforms. There are some which are more suitable, for example, leg robotics or leg robots. With legs, they will be more energy efficient, so you can cover largest areas compared to a flying drone. For higher areas, then you have the problem that you need to reach higher surfaces, so then you have a drone. But if you have very narrow spaces, then a balloon will be a better solution. But you need to make the electronics for the cameras as small as possible, right, and lightweight as possible. So there are a bunch of limitations because it's also harder to control a balloon. Yeah.
One through the chat. So we have a question. It's nice to see how we can use drones for environmental work, like seeing the uncovered places where sunlight can't reach and where it's difficult to reach a human, thanks to Jan and Harley. And the question is it possible to bring something during exploring by drone?
Sorry? What is it? To bring something like an example, for example.
Okay.
Example, for example, yeah.
Get samples. It's technically possible if you have the right payload on your drone. Let's say you have a small holder or a small way to catch objects, you might be able to do it, but that need to account for extra weight, which means more energy, which means higher drones, bigger drones, right? Yeah, this is clear in drones. More payload translate to more space and more weight, and it's actually to the power of 3. That's the scale. Right? If you increase the weight by 1 unit, the size of the drone scale basically to the power of 3. Yeah, this is well known.
You could bring samples.
If you can get samples, yep.
Technically, yes. With a drone, it depends.
Yes.
Thank you very much. Was there another question? Okay. So then we will have our workshop with Antonio. For that we will have to change the seating selection a little bit because the band is going to start setting up here, and then we'll have the workshop probably best in that area or that area back there. We haven't quite figured that logistics out yet, but we need to have 1 or 2 tables, I think, or how many? Yeah, 1 table. So maybe we can just put 1 table there in the, and then maybe face the seats around.
Achso, nee, das wird jetzt das wird ja auch das schalten wir jetzt ab.